You should not exist, not as a philosophical statement, not as existential dread, as a fact of physics. The universe you are sitting in right now, the one that built stars and forged carbon and wove together the atoms in your bones, is balanced on a margin so thin that if you nudged a single dial by a fraction of a percent, none of this would be here. No galaxies, no chemistry, no you. And yet here we are. Every constant that governs reality, every number that decides whether matter holds together or flies apart, landed in the narrow sliver of possibility that allows for existence. Not close, not approximate, exact, precise, impossibly right. The cosmological constant, the term that controls how fast the universe expands, should be 10 to the power of 120 times larger than it is. That is not a typo. That is the worst prediction in the history of physics, and somehow, reality found the one value in a trillion possibilities that lets galaxies form instead of tearing themselves apart in the first fraction of a second. Shift the strong nuclear force by 1% and stars never ignite. Tweak the mass of a neutron by a hair and atoms collapse. Change the energy level inside a dying star by less than 0.5%, and carbon, the element you are made of, never gets built. So what are we supposed to do with that? What does it mean when the cosmos looks less like a random accident and more like a blueprint written specifically so that someone, someday, could stand here and ask why? This is that question. And the answers physics offers are somehow more unsettling than the mystery itself. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. You exist. Let me say that again because the sheer improbability of it deserves repetition. You exist. You are reading this right now, composed of atoms forged in the cores of dying stars, arranged into a structure capable of thought, memory, and the ability to ask why any of this is here at all. And according to the mathematics that govern reality, you shouldn't be. None of this should be. The stars shouldn't shine. Atoms shouldn't hold together. The universe itself, by every reasonable calculation, should have torn itself apart or collapsed back into nothing within the first fraction of a second after it began. The fact that it didn't, that it's still here, that you're still here, is one of the most unsettling puzzles in modern science. And the deeper physicists look into the machinery underneath reality, the more unsettling it becomes. There are numbers buried in the fabric of the cosmos, not the kind of numbers you learnt in school, not measurements of mass or distance or temperature, though they're related to all of those things. These are deeper. They're the settings, the dials, the coefficients that determine how forces behave, how particles interact, how energy and matter organize themselves into stars and planets, and eventually people who can look up at the night sky and wonder where it all came from. Physicists call them fundamental constants. And what makes them fundamental is that they aren't derived from anything more basic, they just are. The speed of light is roughly 299,792,458 meters per second. The strength of the electromagnetic force, the one that holds electrons in orbit around atomic nuclei, is described by a number called the fine structure constant, approximately 1 divided by 137. The mass of an electron is about 9.1 times 10 to the negative 31st kilograms. These aren't rounded for convenience. They're measured values, carved into the bones of reality itself. Change them even slightly, and everything breaks. For most of human history, we had no idea these numbers existed. The ancient Greeks knew about geometry, the motion of planets, the behavior of levers and pulleys. Newton gave us gravity and motion. Maxwell unified electricity and magnetism. Einstein bent space and time into a single fabric. But it wasn't until the 20th century, when quantum mechanics and relativity collided with cosmology, that scientists began to notice something strange. The universe didn't just obey laws, it obeyed laws that seemed to be walking a tightrope. A universe that allowed for complexity, for chemistry, for the slow, patient assembly of molecules into living cells, required not just any set of physical laws, it required this set, this precise configuration of forces and masses and coupling strengths. Shift any one of them by a few percentage points, and the whole structure collapses. Let's start with something simple: the electromagnetic force. It's what keeps electrons bound to atomic nuclei, what allows atoms to link into molecules, what makes chemistry possible. If that force were just 4% stronger, the sun would have burned out long before life had time to evolve on Earth. The fusion reactions in its core would proceed too quickly, converting hydrogen into helium at a pace that would exhaust the fuel supply in a geological blink. A star like ours, instead of shining steadily for 10 billion years, would flare out in a few 100 million. Not enough time for single-celled organisms to crawl out of the ocean, let alone build telescopes and particle accelerators and start asking uncomfortable questions about their own existence. Make the electromagnetic force 4% weaker, and a different problem emerges. Carbon, the element that forms the backbone of every living thing you've ever known, becomes almost impossible to produce. The nuclear reactions inside stars that fuse helium into carbon depend on a delicate resonance, a precise alignment of energy levels that allows the process to happen efficiently. Weaken the electromagnetic force, and that resonance shifts. The carbon production rate drops. Stars churn out less of it. The universe ends up with a lot of helium and not much else. No carbon means no organic molecules, no DNA, no proteins, no enzymes, no metabolism, just a cold universe full of hydrogen and helium, sterile and empty. Now consider gravity. It's the weakest of the four fundamental forces by an almost absurd margin. The electromagnetic force is roughly a trillion times stronger. You can feel this difference directly. A cheap refrigerator magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire planet. But gravity's weakness is what makes life possible. If gravity was stronger by even a small factor, stars would collapse more aggressively during formation. They'd burn hotter, faster, and die younger. A star like the Sun might last only a few million years instead of billions. Again, not enough time for biology to get anywhere interesting. Even worse, planets orbiting such stars would be subjected to more intense radiation and tidal forces. The habitable zones around them would shrink to razor-thin bands. Step a little too close and your world is scorched. Drift a little farther out and it freezes. Weaken gravity, and the universe has a different set of problems. Galaxies wouldn't form, stars wouldn't ignite, gas clouds would just drift forever, too diffuse to collapse under their own weight. Without stars, there's no fusion, no heavy elements, no planets, no chemistry, just an endless fog of hydrogen slowly spreading into the dark. Then there's the strong nuclear force, the one that holds atomic nuclei together. Protons inside a nucleus are positively charged. They repel each other electromagnetically. The strong force is what overpowers that repulsion, binding protons and neutrons into stable arrangements. If the strong force were just 2% weaker, deuterium, a form of hydrogen with one proton and one neutron, wouldn't hold together. Deuterium is a critical stepping stone in the fusion chain that powers stars. Without it, stellar fusion stalls. No fusion means no energy generation, no heavy element production, no light. The universe goes dark. Make the strong force 2% stronger and you get the opposite problem. Deuterium becomes too stable. Protons start sticking together more aggressively. In the early universe, during the first few minutes after the Big Bang, when temperatures were still high enough for fusion to occur everywhere at once, nearly all the hydrogen would have been burned into heavier elements. By the time things cooled down, there'd be almost no hydrogen left. No hydrogen means no water, no long-lived stars like our Sun, which burn hydrogen for billions of years. Just a universe full of helium and heavier elements, glowing briefly and then fading into darkness. Each of these forces, these constants, sits in a narrow range that allows for a universe capable of supporting the kind of structure and complexity that life requires. Step outside that range in any direction and something critical breaks. Stars don't form, elements don't assemble, chemistry doesn't happen. It's not that life as we know it becomes slightly less likely. It's that the preconditions for any form of chemistry-based complexity vanish entirely. This wasn't obvious at first. Early 20th century physicists were too busy figuring out the rules to notice how improbably well-tuned the rules appeared to be. The focus was on discovery, on building the frameworks of quantum mechanics and general relativity, on testing predictions, on mapping the subatomic zoo of particles that kept popping out of accelerators. The fine-tuning problem only came into focus later as precision cosmology matured. By the 1980s and 1990s, scientists had measured the fundamental constants to extraordinary accuracy. They'd calculated how stars burn, how nuclei form, how galaxies assemble. And once the data was in, once the models were refined, the picture became uncomfortably clear. The universe appears to be balanced on a knife's edge. Martin Rees, a cosmologist at Cambridge, distilled the problem into what he called 6 numbers, 6 dimensionless constants that describe the large-scale structure and behavior of the universe. The ratio of the strength of gravity to the electromagnetic force, the amount of matter in the universe, the density of dark energy, the amplitude of primordial density fluctuations that seeded galaxy formation, the number of spatial dimensions. Each one had to fall within a surprisingly narrow range for a universe like ours to exist. Rees put it plainly. The values of these numbers seem to have been finely adjusted to make possible the development of life. Not slightly adjusted, finely adjusted. The kind of precision you'd expect from an engineer, not from a random roll of cosmic dice. Other physicists echoed the sentiment. The Stanford Encyclopedia of Philosophy defines fine-tuning as phenomena depending sensitively on parameter values falling within extremely narrow ranges. Sensitively narrow. Those aren't dramatic words. They're technical ones, and that's what makes the observation so difficult to dismiss. This isn't mysticism, it's math. Run the simulations with slightly different constants, and the universes that pop out on the other side are dead on arrival. No stars, no planets, no chemistry, no observers to wonder why things went wrong. The most extreme example of this knife-edge balance is something called the cosmological constant problem, and it involves a number so spectacularly wrong that it has become the single most embarrassing mismatch between theory and observation in the history of physics. That number is 10 to the power of 120. To give you a sense of scale, the number of atoms in the observable universe is somewhere around 10 to the 80. The number of seconds since the Big Bang is about 10 to the 18. 10 to the 120 is a number so large that if you tried to write it out in full, with every zero carefully placed, you'd run out of space long before you finished, even if you used every particle in the universe as ink. Steven Weinberg, a Nobel Prize-winning physicist, is widely quoted as saying the cosmological constant appears fine-tuned to 1 part in 10 to the 120. What he's referring to is the vacuum energy of space itself. Quantum field theory predicts that even empty space should be seething with energy, a roiling quantum foam of particles and antiparticles popping in and out of existence at scales far too small and fast to observe directly. When physicists calculate how much energy that foam should contribute to the universe, they get an answer, a very large answer. The problem is that when they measure the actual energy density of space using cosmological observations, the number they get is roughly 120 orders of magnitude smaller than the prediction. It's not a little bit off. It's not even close. It's the worst prediction in the history of science. If the vacuum energy were as large as quantum theory predicts, the universe would have blown itself apart almost instantly after the Big Bang. Space would be expanding so fast that matter could never clump together. No galaxies, no stars, no planets, no anything. Just a rapidly diluting fog of particles spreading into oblivion. The fact that we're here, that galaxies exist, that stars burn and planets orbit and life has time to evolve and build civilizations capable of doing the math that reveals this problem in the first place, means the vacuum energy has to be almost exactly zero. Not zero, because we've measured a tiny positive value, the thing we now call dark energy, but close enough to zero that the universe can survive long enough to become interesting. The cancellation required to bring the predicted value down to the observed value is precise to 1 part in 10 to the 120. That level of precision is like balancing a pencil on its tip, on top of another pencil balanced on its tip, on top of a third pencil, and continuing that stack across the entire width of the Milky Way galaxy, and having it not fall over. Nobody knows why the cancellation happens. There's no known mechanism in physics that would naturally drive the vacuum energy that close to zero. It just is. And the fact that it is, the fact that this universe managed to land on a value that sits in the one narrow sliver of parameter space where structure and complexity are possible, is what physicists mean when they talk about fine-tuning. It's not that the constants are beautiful or elegant. It's that they are sitting exactly where they need to be for anything to exist at all. Move the dial a fraction in any direction, and the universe either collapses, tears itself apart, or settles into a lifeless equilibrium. This wasn't a problem anyone expected to find. Early cosmology focused on broad theoretical questions. What happened in the first moments after the Big Bang? How did galaxies form? Why is the universe expanding? The fine-tuning issue only surfaced once the tools became precise enough to measure the constants and model what would happen if they were different. And once that door opened, it didn't close. The more physicists looked, the more examples they found. The masses of particles, the strengths of forces, the rates of nuclear reactions, all of them sitting in suspiciously narrow ranges that permit the existence of a universe capable of producing observers. Brian Greene, a physicist and science communicator, has described the issue as a major cosmological mystery, calling the universe exquisitely tuned for life. Exquisitely, that's a strong word. It's the kind of word you use when precision isn't accidental, and that's where the discomfort comes from. Because if the constants aren't accidental, if they're the result of some deeper organizing principle, then what is that principle? And if they are accidental, if the universe really did just happen to roll the dice and land on the one combination out of 10 to the 120 possibilities that allows for stars and chemistry and biology, then we're left staring at a coincidence so staggering that it feels less like an explanation and more like a placeholder for something we haven't figured out yet. The fine-tuning problem sits at the intersection of physics, philosophy, and a kind of existential vertigo. It forces a question that science usually tries to avoid. Why this universe? Why these constants? Why this narrow corridor of parameter space where matter can organize itself into galaxies and stars and planets and eventually into systems complex enough to ask why they exist? For most of history, those questions belonged to religion or metaphysics. Science dealt with how things worked, not why they were there to work in the first place. But modern cosmology has dragged the why question out of the shadows and dumped it on the table in the form of numbers that refuse to behave. There are answers on offer, some of them radical, some of them uncomfortable, none of them universally accepted. The debate is still live. The explanations range from the existence of countless other universes, each with different constants, to the possibility that we're observing a selection effect, to the idea that something deeper in the laws of physics constrains the constants in ways we don't yet understand. And then there are the explanations that step outside the boundaries of science entirely: design, simulation, a universe crafted deliberately by something with intent. Those ideas make physicists nervous, not because they're impossible, but because they're untestable. Science works by making predictions, running experiments, comparing results. If the answer to why the constants are finely tuned is that someone or something set them that way, there's no experiment you can run to confirm or refute it. The conversation stops. But the numbers don't stop. They keep sitting there, measured to dozens of decimal places, refusing to budge. The cosmological constant is almost exactly what it needs to be. The strong force is precisely strong enough. Gravity is weak in exactly the right way. The mass of the electron, the charge of the proton, the expansion rate of space itself, all of them threaded through a parameter space so narrow that missing the target by a hair would render the universe uninhabitable. And yet here we are, not almost here, fully here. Thinking, measuring, wondering how we ended up in a cosmos that seems to have been waiting for us. That waiting is the eerie part. The universe didn't have to allow for complexity. It didn't have to permit the formation of heavy elements or stable atoms or long-lived stars. It could have been simple: a fog of particles, a brief flash of energy, a quick collapse into nothing. Instead, it built a stage. A vast, ancient, intricate stage on which matter learned to organize itself into stars, planets, oceans, cells, neurons, thoughts. And every piece of that stage rests on a foundation of constants that could have been different but aren't. The question of what comes next, of how to make sense of this knife-edge balance, doesn't have a clean answer yet, but it has a starting point. And that starting point is a number so absurdly large, so impossibly precise, that it has become the symbol of everything strange about the universe's apparent calibration. 10 to the 120, the cosmological constant mismatch. The single most glaring example of fine-tuning in all of modern physics. And if you want to understand why you exist, why any of this exists, that number is where the story begins. The cosmological constant is the number that should have killed you before you were born, before your parents were born, before the Earth formed, before the first star ignited, before the universe had time to do anything interesting at all. It is a term in Einstein's equations of general relativity, represented by the Greek letter lambda, and it describes something that sounds innocent until you dig into what it actually does. It measures the energy density of empty space itself, not the energy of particles or fields or radiation. the energy of nothing, the vacuum. And according to every calculation physicists know how to perform, that energy should be so catastrophically large that the universe would have torn itself apart in the first fraction of a second after the Big Bang, ripping space into shreds before a single atom had time to form. It didn't. The universe is still here. You are still here. And the reason that's true is that the cosmological constant, against all theoretical expectations, is almost exactly zero. Not zero, because we've measured a tiny positive value, but small enough that the universe had time to cool, to let matter clump together under gravity, to build galaxies and stars and planets and eventually produce observers capable of noticing how impossibly lucky they are to exist. The mismatch between what the constant should be and what it actually is represents the single worst prediction in the history of physics. Not off by a little, not off by a factor of 2 or 10 or even 1,000, off by a factor of 10 to the power of 120. Let's be clear about what that means. 10 to the 120 is not a number humans have intuition for. The number of atoms in the observable universe is about 10 to the 80. The number of seconds since the Big Bang is around 10 to the 18. The number of grains of sand on every beach on Earth is somewhere near 10 to the 24. 10 to the 120 is so large that if you tried to count to it, advancing one number per second, you would still be counting long after every star in the universe had burned out, long after the last black hole had evaporated, long after the cosmos itself had faded into a cold, dilute fog of radiation. You would not be remotely close. That is the size of the error. Theory predicts a cosmological constant around 10 to the 120 times larger than what we observe. And if theory were right, if the constant actually had the value quantum mechanics says it should, the universe would have lasted roughly 10 to the negative 30 seconds. A decimal point followed by 29 zeros and then a 1, shorter than the time it takes light to cross the diameter of a proton. In that sliver of time, space itself would have expanded so violently that no structure of any kind could form. No particles would bind together. No forces would have time to act. The cosmos would just blow itself apart and be done with it. The story of how we ended up with this problem starts in 1915, the year Einstein published his general theory of relativity. The equations were beautiful, elegant, and they described gravity not as a force pulling objects together, but as the curvature of space-time itself. Mass and energy warp the fabric of space, and objects moving through that warped space follow curved paths. It was a complete reimagining of how the universe worked. But there was an issue. When Einstein applied his equations to the universe as a whole, he found that they wouldn't sit still. The solutions kept insisting that space itself had to be either expanding or contracting. A static universe, the kind everyone at the time assumed we lived in, wasn't stable under general relativity. Einstein didn't like that. The observational evidence of his day suggested the universe was eternal and unchanging. So he added a term to his equations, a kind of mathematical fudge factor, to hold everything in place. He called it the cosmological constant. It acted as a repulsive force, a kind of anti-gravity that pushed space apart just enough to balance out the attractive pull of matter and keep the universe static. The constant had no deeper justification. It was there because Einstein needed it to be there to match what he thought the universe looked like. Then, in 1929, Edwin Hubble published observations showing that distant galaxies were moving away from us. The universe wasn't static, it was expanding. Einstein reportedly called the cosmological constant his biggest blunder. He removed it from the equations, and for decades, most physicists assumed lambda was simply zero. Problem solved. The universe expands because it started from a hot, dense state and has been coasting outward ever since. No need for an extra term. The constant came back. Not because someone wanted it to, but because the universe forced the issue. In 1998, two independent teams of astronomers were measuring the distances and velocities of distant supernovae, trying to figure out how much the expansion of the universe had been slowing down over time. Gravity pulls everything together, so the expectation was that the expansion rate should be decelerating. The more matter in the universe, the stronger the braking effect. The measurements were supposed to settle how much matter there was, and whether the universe would eventually stop expanding and collapse back in on itself, or keep expanding forever at a gradually slowing pace. The data said something else. The expansion wasn't slowing down, it was speeding up. Distant galaxies were accelerating away from us. Something was pushing space apart, and whatever it was getting stronger as the universe aged. The result was so unexpected that both teams spent months checking for errors before publishing. There were no errors. The acceleration was real. And the simplest explanation, the one that fit the data cleanly, was that Einstein's cosmological constant wasn't zero after all. It was small but positive. Space itself carried a tiny intrinsic energy, and that energy was driving the expansion faster and faster. The discovery earned the leaders of both teams the Nobel Prize in Physics in 2011. It also reopened one of the deepest problems in theoretical physics. Because once you accept that the cosmological constant is real, you have to explain where it comes from. And that's where quantum field theory enters the picture, carrying an answer so spectacularly wrong that it has defined the vacuum energy problem ever since. Quantum field theory is the framework that describes how particles and forces behave at the smallest scales. It's the foundation of the standard model of particle physics, and it has been tested to extraordinary precision. One of its central insights is that empty space isn't really empty. The vacuum is filled with fields, quantum fields for every type of particle that exists, and those fields fluctuate. Even in the absence of real particles, virtual particles pop in and out of existence constantly, borrowing energy from the vacuum for fractions of a second before annihilating and paying it back. These fluctuations are not hypothetical. They produce measurable effects, like the Casimir force, where two metal plates placed close together in a vacuum experience a tiny attractive force because the space between them suppresses certain wavelengths of virtual particles. Every fluctuating field contributes energy to the vacuum. Add up all the contributions from all the fields in the standard model, and you get a number, a very large number. The calculation isn't perfectly clean because the integral diverges at high energies, meaning the result depends on where you cut off the sum. The usual choice is to cut it off at the Planck scale, the energy scale where quantum mechanics and gravity are expected to merge into a theory we don't have yet. That cutoff sits at about 10 to the 19th gigaelectron volts. Plug that into the calculation, and the predicted vacuum energy density comes out to roughly 10 to the 113 joules per cubic meter. The observed value, the one we measure by looking at how fast the universe is expanding, is about 10 to the negative 9 joules per cubic meter. The difference between prediction and observation is 10 to the 122. Some sources round it to 10 to the 120. Others say 10 to the 121. The exact number depends on conventions and units. The point is, it's an error so large that it makes every other mistake in physics look like a rounding error. Steven Weinberg, who won the Nobel Prize for his work on unifying the electromagnetic and weak nuclear forces, has called this the greatest failure of an order of magnitude estimate in physics. Frank Wilczek, another Nobel laureate, described it as a veritable crisis. The Stanford Encyclopedia of Philosophy puts it plainly, calling it the worst prediction in physics. Not wrong, not imprecise, the worst. This is not a niche issue confined to obscure corners of theoretical work. It sits at the intersection of our two best theories, quantum mechanics and general relativity, and it tells us that something fundamental is broken. The mismatch isn't just an academic embarrassment. It's an existential puzzle, because the value we observe, tiny as it is, sits in the one narrow range that allows for a universe capable of forming structure. If the cosmological constant were larger, even modestly larger, the repulsive effect of vacuum energy would overpower gravity long before galaxies had time to form. Matter would never clump together, stars would never ignite, planets would never coalesce. The universe would just expand faster and faster, diluting into a cold, empty void within a few million years. Make the constant 10 times larger than the observed value, and galaxies don't form. 100 times larger, and even the seeds of structure planted in the early universe by quantum fluctuations wouldn't have time to grow. 1,000 times larger, and matter would be ripped apart almost as soon as it cooled enough to exist. The threshold isn't generous, it's razor thin. The observed value of the cosmological constant sits right at the edge of what a universe capable of producing complexity can tolerate. Flip the sign, make the constant negative, and you get a different catastrophe. Negative vacuum energy would act as an attractive force, pulling space together instead of pushing it apart. A small negative constant would cause the universe to recollapse quickly, running the Big Bang in reverse and ending in a big crunch before stars had time to form. The window between too much expansion and too much contraction is vanishingly small, and somehow the universe landed in that window. What makes this especially uncomfortable is that the cosmological constant has no reason to be small. In most physical systems, when something cancels to high precision, there's a symmetry or conservation law driving the cancellation. Electric charge is conserved, energy is conserved. Certain quantities in particle physics are protected by symmetries that force them to take specific values. The cosmological constant has no such protection. Every contribution to the vacuum energy from every particle and field in the universe should add up. The electron contributes, the photon contributes, the Higgs field contributes. Quarks, gluons, neutrinos, W and Z bosons, all of them dump energy into the vacuum, and there's no known symmetry that forces those contributions to cancel, yet they do cancel. Almost perfectly, to 120 decimal places. It's as if you took 100 random numbers, each with 100 digits, some positive and some negative, added them all together, and got 0 to within 1 part in 10 to the 120. That doesn't happen by accident. But if it's not an accident, what is it? What mechanism could possibly drive such a precise cancellation? Physicists have proposed dozens of solutions over the years. Some involve modifying general relativity at large scales to change how vacuum energy affects the expansion of space. Others suggest new symmetries or fields that might suppress the contributions from quantum fluctuations. A few argue that the problem is an artifact of how we're doing the calculation, that we're double counting something or applying quantum field theory in a regime where it doesn't apply. None of these ideas have gained widespread acceptance. Most of them introduce new problems as severe as the one they're trying to solve. One approach that gained traction in the 1980s and 1990s was called supersymmetry. It proposed that every particle in the standard model has a partner particle with slightly different properties. The partners haven't been observed yet, but if they exist, their contributions to the vacuum energy would come in with opposite signs from the standard model particles. Bosons contribute positively. Fermions contribute negatively. In a perfectly symmetric setup, the contributions cancel exactly. The cosmological constant becomes zero, except it's not zero. It's small, but positive. So even if supersymmetry exists, it has to be broken. The partner particles have to be heavier than the standard model particles, which ruins the exact cancellation and leaves behind a leftover vacuum energy. And unless the breaking happens in a very specific and finely tuned way, you still end up with a cosmological constant that's way too large. The Large Hadron Collider at CERN has spent years searching for signs of supersymmetric particles and hasn't found any. The idea isn't dead, but it's under serious strain. Another possibility is that the vacuum energy we observe isn't coming from quantum fluctuations at all. Maybe it's a property of a field we haven't discovered yet, a field that's slowly rolling down a potential energy hill, changing its value over cosmic time. Physicists call this idea quintessence. It would allow the effective cosmological constant to vary, which might explain why we're observing it at this particular moment in cosmic history, rather than at some other time when it might have been much larger or smaller. The problem is, quintessence models require yet another finely tuned field, one that has to start with just the right initial conditions and roll at just the right rate to match observations. You're replacing one fine-tuning problem with another. The most radical solution, the one that has generated the most debate and the least consensus, is to accept that the cosmological constant really is randomly selected, and that we live in the one universe where it happened to land on a value compatible with life. This is the anthropic explanation, and it requires the existence of a multiverse, a vast ensemble of separate universes, each with different physical constants. In that framework, most universes have cosmological constants far too large or far too small to allow for structure. Those universes are sterile, lifeless, devoid of observers. We don't live in one of those universes because we can't. We live in one of the rare pockets where the constant happened to be small enough for galaxies and stars, and eventually life to emerge. The fact that we find ourselves in such a universe is a selection effect, not a mystery. That explanation bothers a lot of physicists. Weinberg himself has worked on anthropic arguments, but even he has noted the discomfort they provoke. The multiverse hypothesis is hard to test. If other universes exist but are causally disconnected from ours, there's no experiment you can run to confirm or refute their existence. You're left with a framework that explains the data but offers no way to make predictions. Some see it as giving up on finding a deeper mechanism. Others argue it's the only honest answer to a problem that has resisted every other solution for decades, and yet the number sits there. 10 to the 120, the size of the discrepancy between what quantum mechanics predicts and what the universe actually does. It's printed in textbooks, cited in papers, discussed at conferences. It has been called the elephant in the room of modern cosmology. Leonard Susskind, a theoretical physicist at Stanford and one of the architects of string theory, has described the cosmological constant problem as the mother of all physics problems. Not a puzzle, not a challenge, a problem. The kind that defines entire careers and remains unsolved across generations. The fact that the constant is small enough to permit structure, but large enough to be detectable, has another strange feature. We're living at almost the only epoch in cosmic history when both matter and dark energy are significant. In the early universe, matter dominated. The cosmological constant was always there, but its effects were swamped by the density of radiation and matter packed into a much smaller volume. In the far future, dark energy will dominate completely. The expansion will accelerate so much that galaxies will be ripped apart, stars will drift beyond each other's horizons, and the universe will become a lonely, empty expanse. The window when both matter and dark energy are comparable, when galaxies are still forming and stars are still shining, but the acceleration is also measurable, lasts only a few billion years, and we happen to be living in it. That timing coincidence has led some researchers to wonder whether the anthropic explanation has an extra layer. Maybe the cosmological constant isn't just compatible with life in general. Maybe it's constrained by the requirement that observers emerge at a time when they can actually measure it. If we'd appeared much earlier or much later, the universe would look simpler, and the fine-tuning problem might never have been noticed. This version of the argument is even more speculative, and it pushes the boundaries of what science can address without tipping into philosophy. What's not speculative is the measurement. The acceleration of the universe's expansion is real. It's been confirmed by multiple independent methods: observations of distant supernovae, measurements of the cosmic microwave background, studies of galaxy clustering, and maps of large-scale structure all point to the same conclusion. Space is being pushed apart by something, and that something behaves exactly like a cosmological constant, with a value of about 10 to the negative 52 per square meter in geometric units. Tiny, but not zero, and sitting exactly where it needs to be for the universe to have a long, interesting history. If lambda were just slightly larger, structure formation would shut down. Stars would still be shining now, but they'd be the last generation. No new galaxies would form. The universe would coast into an accelerating expansion that would eventually isolate every star system, every galaxy, every structure, leaving them as islands in an ever-expanding sea of space. If lambda were even moderately larger, those islands wouldn't exist at all. The universe would have expanded too fast for gravity to ever pull matter together in the first place. The cosmological constant is not the only fine-tuning problem in physics, but it's the most extreme. It's the one where the numbers are so lopsided that they stop feeling like science and start feeling like a cosmic joke. And it's the one that has forced physicists to ask questions they'd rather not ask. Questions about whether the laws of physics are inevitable or contingent, whether the constants could have been different, whether there's a reason they landed on the values they did, or whether we're just staring at the result of an unimaginably lucky roll of the dice. The error bars on the measurement have shrunk over the years. The value is known now to within a few percent. The theoretical prediction hasn't budged. Quantum field theory still says the vacuum energy should be enormous. Observation still says it's almost nothing. The gap hasn't closed. If anything, it's become more precise, more well-defined, more impossible to ignore. And with that precision comes a stark realization. Either our understanding of quantum mechanics is missing something fundamental, or our understanding of gravity is, or the universe is part of a much larger structure that we can't see and may never be able to test. None of those options are comforting. All of them demand answers that go beyond the current boundaries of science. The cosmological constant problem is not going to be solved by better telescopes or more powerful particle accelerators. It's a problem at the foundation, a crack in the bedrock, a number that tells us we're missing something big. And until we find it, that number will keep sitting there, 10 to the 120, the worst prediction in the history of physics, and the clearest signal we have that the universe we live in is balanced on a knife's edge we don't yet understand. The cosmological constant is the headline act, the number so wrong it became famous. But it's not alone. The universe didn't stop at getting one constant right. It got dozens of them right, threading the needle on parameter after parameter in ways that shouldn't work if everything were random. And nowhere is that more obvious than in the stars. because stars are not just balls of burning gas, they're factories. Alchemical engines that take the simplest element in the universe and forge it into everything else. Hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, all the way up the periodic table to iron. Every atom in your body heavier than hydrogen was built inside a star, and the process that built it depends on a series of nuclear reactions so finely calibrated that shifting any of the underlying constants even slightly would shut the whole operation down. Start with carbon. It's the fourth most abundant element in the universe after hydrogen, helium, and oxygen. It's the backbone of organic chemistry, the element that can bond to itself in long chains and rings, forming the structural foundation for proteins, DNA, carbohydrates, fats, every molecule that makes biology possible. Life as we know it is carbon-based, not because we lack imagination, but because carbon is uniquely suited to the job. It's stable, versatile, and abundant. Without it, chemistry becomes far less interesting. The molecules you can build from hydrogen, helium, and oxygen alone are limited. Water, hydroxide, hydrogen peroxide, useful, sure, but not enough to build a cell, let alone a brain. So where does carbon come from? Not from the Big Bang. The early universe produced hydrogen, helium, and traces of lithium. That's it. Everything heavier had to wait for the first stars to light up, to compress and heat matter to the point where nuclear fusion could begin assembling heavier elements. And the process that makes carbon is not straightforward. It's a three-step dance that requires precise timing, specific energy levels, and a resonance that sits in exactly the right place to make the whole thing work. The fact that it works at all is strange. The fact that it works efficiently enough to fill the universe with carbon is borderline miraculous. Here's the problem. You can't make carbon directly from hydrogen. You need helium first. And once you have helium, you can't just slam two helium nuclei together and get carbon. Helium-4 has 2 protons and 2 neutrons. Fuse 2 of them and you get beryllium-8, which has 4 protons and 4 neutrons. Beryllium-8 is unstable, violently unstable. It falls apart in about 10 to the negative 16 seconds, a time span so short that it barely exists before splitting back into 2 helium nuclei. If you want carbon, which has 6 protons and 6 neutrons, you need to add a third helium nucleus to the beryllium before it decays. The window is impossibly narrow. You're trying to thread a needle while the needle is dissolving. The process is called the triple alpha reaction because helium-4 nuclei are also called alpha particles. 3 alphas combine to make carbon-12, in principle. In practice, the reaction is so improbable that it shouldn't happen often enough to matter. Stars are hot, sure. The cores of red giant stars, where carbon gets made, reach temperatures around 100 million degrees Celsius. At those temperatures, helium nuclei are moving fast, colliding constantly. But most of those collisions do nothing. The nuclei bounce off each other or form beryllium-8 that decays before a third helium can arrive. The rate at which carbon should form from random 3-body collisions is far too slow to explain the amount of carbon we see in the universe. That's where Fred Hoyle comes in. Hoyle was a British astrophysicist, brilliant and combative, the kind of scientist who was right just often enough to make his colleagues nervous when he disagreed with them. In the early 1950s, he was working on the problem of element formation in stars, trying to figure out how the universe ended up with so much carbon. The numbers didn't work. The triple alpha process as it was understood at the time was too slow. Stars should be producing carbon at a trickle, not a flood, and yet carbon was everywhere. In meteorites, in the spectra of distant stars, in the earth beneath his feet. Hoyle reasoned backward from the observation. If carbon exists in large quantities, the triple alpha process has to be faster than the basic calculations predict. And the only way to make it faster is if there's a resonance, a specific energy level inside the carbon-12 nucleus that matches almost exactly the combined energy of the 3 helium nuclei coming together. Think of it like pushing a child on a swing. Push at random times and you do some work, but it's inefficient. Push at the exact moment the swing reaches its peak and you get a much bigger effect for the same effort. A resonance is nature's way of amplifying a process that would otherwise be too weak to notice. Hoyle calculated what the energy of that resonance would have to be if it existed. His prediction was 7.65 mega-electron volts above the ground state of carbon-12. He published the result in 1953 and told experimentalists to go look for it. They did. And in 1957, a team at Caltech, led by Ward Whaling, found it. The resonance was right where Hoyle said it would be, measured at about 7.653 mega-electron volts, accurate to within a fraction of a percent. It's now called the Hoyle state, one of the most famous examples in physics of a prediction made purely on astrophysical grounds, being confirmed in the lab years later. The discovery didn't just vindicate Hoyle, it explained why the universe has carbon. The Hoyle state sits roughly 380 kilo-electron volts above the energy of 3 helium-4 nuclei at rest. That's a tiny sliver of energy in nuclear terms. If the resonance were much higher, the thermal energy of helium nuclei in a stellar core wouldn't be enough to reach it, and the amplification effect would vanish. Carbon production would drop by orders of magnitude. If the resonance were much lower, it would sit below the 3 alpha threshold and wouldn't help at all. The window is narrow, and the universe threaded it. But the story doesn't end with carbon. Once carbon forms, it's sitting in the core of a star, surrounded by a sea of helium nuclei. Some of those helium nuclei are going to collide with the newly formed carbon and fuse into oxygen-16. This is the next step up the nuclear ladder, and it's happening at the same time carbon is being made. The balance between these two processes, carbon formation and carbon destruction, determines the final ratio of carbon to oxygen in the universe. Too much carbon destruction and you end up with a universe full of oxygen and almost no carbon. Too little and you get carbon but not enough oxygen. Both elements are essential for life as we know it. Water is hydrogen and oxygen. Organic molecules are carbon and hydrogen, with oxygen mixed in for functional groups. You need both, and you need them in roughly comparable amounts. The rate at which carbon captures an alpha particle to become oxygen depends on the strength of the nuclear force and the electromagnetic force. These are two of the 4 fundamental forces, and their relative strengths determine the structure of atomic nuclei, the energies of nuclear reactions, the stability of elements. The strong nuclear force is what holds protons and neutrons together inside a nucleus, overcoming the electromagnetic repulsion between positively charged protons. The electromagnetic force is what makes those protons repel each other in the first place. The interplay between attraction and repulsion sets the energy levels, the resonances, the reaction rates. If the strong force were slightly stronger, the resonance that helps carbon form would shift. The Hoyle state might move to a different energy, or new resonances might appear that speed up the conversion of carbon into oxygen. Run the numbers, and you find that a small increase in the strong force leads to a universe where stars burn through their carbon almost as fast as they make it. By the time the star dies and ejects its outer layers into space, seeding the next generation of star formation with heavy elements, there's plenty of oxygen but not much carbon left. The periodic table gets lopsided. chemistry loses one of its most important building blocks. Make the strong force weaker and the opposite happens. The carbon production rate drops. The Hoyle state shifts to a less favorable energy, or the resonance becomes broader and less effective at amplifying the reaction. Stars make less carbon overall, and the universe ends up deficient in both carbon and oxygen because the whole nucleosynthesis chain slows down. Either way, you lose. The balance we observe, where stars produce enough carbon to fill the cosmos and enough oxygen to make water and atmospheres and the chemical backbones of biological molecules, sits in a narrow corridor of parameter space defined by the precise values of the strong and electromagnetic forces. Hoyle himself was struck by this. Later in life, he wrote that the carbon resonance looked like a fix, as if the universe had been deliberately set up to produce the elements life requires. He wasn't invoking a deity, not exactly, but he was pointing at a coincidence so specific that it demanded explanation. The Hoyle state is not approximate. It's not close enough. It's exactly where it needs to be, measured to a precision of a few kilo-electron-volts, to ensure that stars can make carbon efficiently without converting all of it into oxygen. And it's not just carbon and oxygen. The entire chain of element formation in stars depends on a cascade of nuclear reactions, each one sensitive to the masses of particles, the strengths of forces, the energy levels of nuclei. After oxygen comes neon, magnesium, silicon, sulfur, all the way up to iron. Iron is the end of the line for fusion because fusing iron into heavier elements costs energy instead of releasing it. Stars can't sustain fusion past iron. Everything heavier than iron, gold, platinum, uranium, gets made in supernova explosions or neutron star collisions, where the conditions are violent enough to drive reactions that don't happen in normal stellar cores. Every step in that chain has its own set of requirements. The reaction rates have to be fast enough that elements actually get produced before the star runs out of fuel or explodes. The energy levels have to line up so that the reactions are kinetically accessible at the temperatures and densities inside a star. The stability of intermediate nuclei has to be high enough that they don't decay before they can participate in the next reaction. All of these factors depend on the fundamental constants. Change the mass of the proton or the neutron by a few percent. Shift the strength of the electromagnetic force or the strong force by a small amount, and the whole periodic table rearranges itself. Some elements vanish, others become far more common. The mix that supports chemistry and complexity gets scrambled. Take oxygen. It's made when carbon-12 captures an alpha particle. The reaction proceeds through several possible pathways, and the rate depends on the details of the nuclear structure. If the rate is too high, all the carbon gets burned into oxygen and stars don't leave behind enough carbon to seed planets and interstellar clouds. If the rate is too low, oxygen production stalls and you end up with a universe that has carbon but not enough oxygen to make water. The observed ratio of carbon to oxygen in the universe is roughly 1:2, not equal, but close enough that both elements are abundant. That ratio is the result of billions of years of stellar evolution, countless red giants and supernovae, all running the same nuclear reactions under the same physical laws with the same constants. The triple alpha process itself is a marvel of timing. Beryllium-8 lives for about 10 to the -16th seconds before decaying. At the densities and temperatures inside a red giant core, there's a small but non-zero probability that a third helium nucleus will collide with the beryllium during that brief window. When it does, if the energy is right, the system can jump into the Hoyle state, a quasi-stable, excited level of carbon-12 that lasts long enough to decay down to the ground state, producing a stable carbon nucleus. The whole sequence is a three-body reaction funneled through a two-body intermediate and amplified by a resonance that sits in exactly the right place. Miss any one of those steps and the process collapses. Now add another constraint. The temperature inside a red giant core is not infinite. It's high, but it's bounded by the star's mass and the energy released by helium fusion. If the Hoyle state required more energy to reach, the thermal distribution of helium nuclei wouldn't include enough high-energy particles to populate the resonance. The reaction rate would drop exponentially. If the resonance were lower in energy, it might sit below the threshold for 3 helium nuclei to fuse at all, rendering it useless. The tolerance is tight, measured in hundreds of kilo-electron volts out of a total energy budget of millions of electron volts. That's a precision of a few parts in 10,000. Not as extreme as the cosmological constant problem, but still far narrower than you'd expect from a random setting. Hoyle didn't have access to modern computational tools. He did the calculation by hand, working through the nuclear physics and the stellar models with the data available in the early 1950s. The fact that his prediction was correct to within experimental error is often cited as one of the great triumphs of theoretical astrophysics. It's also one of the clearest examples of fine-tuning in action. Hoyle wasn't trying to make a philosophical point. He was trying to solve a practical problem. Why is there so much carbon? And the answer he found was that there's a nuclear resonance sitting in exactly the right spot. He couldn't explain why the resonance was there. He could only point at it and say, if it weren't, we wouldn't be here. That if-then structure is the core of the fine-tuning argument. If the strong force were different, if the Hoyle state had a different energy, if the electromagnetic force changed the spacing of nuclear levels, then the universe would look different. Stars would still burn, at least some of them, but the products of stellar nuclear synthesis would be skewed. The elements necessary for planets, atmospheres, oceans, and biology would be rare or absent. The chemistry that allows for complexity would be stunted, and crucially, there would be no one around to notice, because observers require chemistry, and chemistry requires elements, and elements require stars that can make them. The carbon coincidence is often paired with another observation, the deuterium bottleneck. Deuterium is heavy hydrogen, 1 proton and 1 neutron. It's the first stepping stone in the chain of fusion reactions that powers stars. Hydrogen fuses into deuterium, deuterium fuses into helium-3, helium-3 fuses into helium-4. Without deuterium, the chain doesn't start. The binding energy of deuterium, the energy it takes to hold the proton and neutron together, is about 2.2 mega-electron volts. That's small compared to other nuclei. Deuterium is barely bound, sitting just on the edge of stability. If the strong force were a few percent weaker, deuterium wouldn't bind at all. The proton and neutron would just bounce off each other. No deuterium means no hydrogen fusion, no main sequence stars, no long-lived energy sources. The universe would be dark, filled with gas clouds that never ignite. If the strong force were a few percent stronger, deuterium would be too stable. During the Big Bang, when the universe was hot and dense enough for fusion to happen everywhere at once, protons would have combined into deuterium too efficiently. Almost all the hydrogen would have been burned into heavier elements in the first few minutes, leaving behind a cosmos with no fuel for stars to burn later. Again, you'd get a universe that's dark, just for a different reason. The strong force sits right in between, weak enough that hydrogen survives the Big Bang, and strong enough that stars can fuse it once they form. The margin is narrow. A shift of 2% in either direction breaks one process or the other. And the value we observe is the one that allows for both a universe full of hydrogen and a universe where that hydrogen can power stars for billions of years, giving planets time to form and lifetime to evolve. These are not abstract thought experiments. They're constraints that come directly from nuclear physics and stellar astrophysics. The binding energies, the resonance levels, the reaction cross-sections, all of them have been measured in laboratories and modeled in simulations. The triple alpha process has been studied for decades. The Hoyle state has been examined with particle accelerators, its properties mapped in detail. The connection between nuclear structure and stellar evolution is one of the best understood areas of modern science. And what it tells us is that the elements we depend on are the products of a manufacturing process that only works because the underlying constants are set to very specific values. Change the constants and the periodic table doesn't just shift, it collapses. Run the simulations with a stronger electromagnetic force and carbon production drops because the Hoyle resonance moves out of reach. Run them with a weaker, strong force and oxygen production slows to a crawl because the nuclear reactions that build heavier elements lose efficiency. The Goldilocks zone isn't just about temperature or distance from a star. It's about the fundamental forces themselves, balanced in a way that permits the existence of chemistry, stars, planets, and the long, slow process of building complexity out of simplicity. Hoyle's phrase, a common-sense interpretation of the facts, was that a super-intellect had monkeyed with physics. He didn't mean that literally, or at least he claimed he didn't, but the language is telling. The facts looked monkeyed with, they looked adjusted. Not because they were elegant or beautiful, though they are, but because they worked. The universe produces carbon, it produces oxygen, it produces the elements necessary for rocky planets and liquid water and organic chemistry. And it does so by running a sequence of nuclear reactions that depend on constants fine-tuned to a degree that makes physicists uncomfortable. The discomfort isn't theological, it's methodological. Science works by finding explanations that don't require special pleading, that flow naturally from the laws and initial conditions without needing to assume the outcome in advance. Fine-tuning feels like special pleading. It feels like the constants were chosen to produce a result, which raises the question of who or what did the choosing, or whether there's a deeper principle, something we haven't discovered yet, that forces the constants to take the values they do. There are hints that such a principle might exist. String theory, for example, suggests that the constants we observe are not truly fundamental, but are instead determined by the shape of extra dimensions, the way a vibrating string produces different notes depending on how it's plucked. If that's true, then the constants are emergent properties of a more basic structure, and the fine-tuning problem becomes a question of why the extra dimensions have the shape they do. But string theory has its own issues, including the fact that it predicts a vast landscape of possible configurations, most of which lead to universes nothing like ours. You're trading one fine-tuning problem for another, asking why we ended up in this corner of the landscape instead of one of the 10 to the 500 others. Loop quantum gravity offers a different approach, quantizing space itself and potentially explaining the cosmological constant as a result of discrete space-time structure. But loop quantum gravity is still a framework under construction, with many open questions and few testable predictions. The anthropic principle, the idea that we observe the constants we do because only those constants permit observers, is a fallback explanation that many physicists accept reluctantly. It works in the sense that it's consistent with the data, but it doesn't feel like an explanation. It feels like a tautology. We're here because we're here. The Goldilocks metaphor, just right, captures the eerie precision of the situation. Not too hot, not too cold, not too much carbon, not too much oxygen, not too strong, not too weak. Every dial turned to the setting that allows for a universe that can host stars, chemistry and life. And the more dials you find, the more unsettling the picture becomes. The cosmological constant is the most famous example. The Hoyle state is the most precise, but there are dozens of others. The mass of the electron, the strength of the weak nuclear force, the rate of expansion in the early universe, the density of dark matter, the amplitude of primordial fluctuations that seeded galaxies. Each one sits in a narrow range, and each one is necessary. Move any of them outside that range, and something critical breaks. The fact that all of them sit where they do, that the universe managed to land on a configuration that works, is what drives the fine-tuning debate. Because the alternative, that it's all just luck, that we rolled the dice and happened to get a universe capable of making stars and carbon and water and DNA, feels less like an answer and more like an admission that we don't have one. The universe makes carbon and oxygen because the Hoyle state sits at exactly the right energy level. That's the headline. But zoom in closer and the machinery underneath becomes even stranger. Because the Hoyle state, the triple alpha process, the entire chain of stellar nucleosynthesis that builds the periodic table, all of it rests on a foundation one layer deeper. The forces that hold matter together in the first place, the strong nuclear force that binds protons and neutrons into atomic nuclei, the electromagnetic force that keeps electrons in orbit around those nuclei, the gravitational force that pulls gas clouds together and ignites stars, and the precise masses of the particles involved, protons, neutrons, electrons, each one sitting at a value that seems chosen to make the whole system work. Change any one of those settings, and the universe doesn't just produce less carbon or run out of hydrogen a little faster. It stops functioning as a place where atoms can exist in stable forms, where chemistry can happen, where stars can burn long enough to forge elements, and planets can hold together long enough for anything interesting to evolve on their surfaces. The constants are not independent variables you can tweak one at a time. They are part of a tightly coupled system, a web of relationships where adjusting one parameter cascades through the others and breaks something critical downstream. This is not fine-tuning in the sense of making things prettier or more efficient. It is fine-tuning in the sense that the universe is walking a tightrope over a void, and the tightrope is about as wide as a hydrogen atom. Start with the strong nuclear force. It is, as the name suggests, strong. The strongest of the four fundamental forces, though its range is microscopic. It only operates over distances comparable to the size of an atomic nucleus, about 1 femtometer, which is 10 to the minus 15 meters, a millionth of a billionth of a meter. At that scale, the strong force is what holds quarks together inside protons and neutrons, and it is what binds protons and neutrons together into stable nuclei. Without it, atomic nuclei would not exist. Protons are positively charged. They repel each other electromagnetically. Pack 2 protons into a nucleus, and the electromagnetic force is trying to blow them apart. Pack 100 protons in there, and the repulsion is enormous. The strong force is what overpowers that repulsion, gluing the nucleus together, despite the fact that every proton inside it is being pushed away by every other proton. The strength of the strong force is not a number you derive from something deeper. It is a measured value, one of the fundamental constants of nature, and it sits in a very narrow range that allows for the existence of stable nuclei across a wide span of the periodic table. Make the strong force even slightly weaker, say 2% weaker, and the balance tips. Deuterium, The simplest nucleus after plain hydrogen consists of one proton and one neutron. The binding energy that holds them together is about 2.2 million electron volts, which sounds like a lot until you realize that is actually one of the smallest binding energies of any nucleus. Deuterium is barely bound. It sits right on the edge of stability. Weaken the strong force by 2% and deuterium falls apart. The proton and neutron do not stick. They bounce off each other and drift away. That might not sound catastrophic. Deuterium is not a common element. You do not find much of it lying around, but deuterium is a bottleneck. It is the first step in the proton-proton chain, the sequence of fusion reactions that powers stars like the Sun. Hydrogen fuses into deuterium. Deuterium fuses into helium-3. Helium-3 fuses into helium-4. Without deuterium, the chain does not start. No fusion means no energy generation. Stars do not ignite. Gas clouds collapse under their own gravity, heat up briefly, and then just sit there, dark and inert. The universe fills with brown dwarfs, failed stars that never got hot enough to sustain fusion. No starlight, no ultraviolet radiation to ionize gas and drive chemistry in interstellar clouds. No long-lived energy sources to warm planets. The cosmos goes dark within a few 100 million years of the Big Bang and stays that way. Make the strong force stronger and you get a different problem. If the strong force were 2% stronger, nuclei would bind more tightly. That sounds good until you think through what it means. During the Big Bang, in the first few minutes after the universe began, temperatures were high enough for nuclear fusion to happen everywhere at once. Protons collided and fused into deuterium, deuterium into helium, helium into heavier elements. But the process only ran for a short time, maybe 3 or 4 minutes, before the universe expanded and cooled enough that fusion stopped. By the time things settled, about 75% of the mass was still hydrogen. 25% was helium. Everything else, all the heavier elements, existed only in trace amounts. That leftover hydrogen is what fuels stars for billions of years afterward. Without it, stars burn out fast and the universe ages rapidly. If the strong force were stronger, deuterium would be more stable, and the fusion reactions in the early universe would proceed more efficiently, too efficiently. Instead of 75% hydrogen and 25% helium, you would end up with something closer to 0% hydrogen and 100% helium and heavier elements. All the hydrogen would have been burned up in the Big Bang itself, converted into helium before the first stars even had a chance to form. No hydrogen means no water, no fuel for stars, no long-lived main sequence stars like the Sun that burn steadily for 10 billion years. Just a universe full of helium, glowing briefly as it collapses into white dwarfs and neutron stars, and then fading into darkness. The tolerance is narrow. The strong force has to be weak enough that deuterium barely binds, so hydrogen survives the Big Bang, and strong enough that deuterium does bind, so stars can fuse hydrogen once they form. The range that allows for both is a few % at most. Shift outside that range, and one process or the other fails, and once that happens, the rest of the structure collapses. No stars means no nuclear synthesis. No nuclear synthesis means no carbon, no oxygen, no heavy elements, no chemistry, no planets, no observers. Now add another layer. The strong force does not operate in isolation. It interacts with the electromagnetic force, and the balance between them determines the structure of atomic nuclei. The electromagnetic force is what makes protons repel each other. It is also what holds electrons in orbit around nuclei, creating atoms and enabling chemistry. The strength of the electromagnetic force is described by a dimensionless number called the fine structure constant, approximately 1 divided by 137. That number shows up in quantum electrodynamics, the theory that describes how light and matter interact. It governs the spacing of energy levels in atoms, the rates of chemical reactions, the way electrons move through materials, change it, and chemistry changes. If the electromagnetic force was stronger by just a few percent, the repulsion between protons in a nucleus would increase. The strong force would have to work harder to hold the nucleus together. Some nuclei that are stable in our universe would become unstable. Larger atoms, the ones with many protons, would be especially affected because the electromagnetic repulsion scales with the square of the number of protons. A nucleus with 10 protons has 100 units of repulsion. A nucleus with 50 protons has 2,500. Add even a small amount to the electromagnetic force, and the heaviest elements start to fall apart. The periodic table gets shorter. Anything past, say, silicon or sulfur might not hold together long enough to matter. No iron, no nickel, no heavier metals. And since rocky planets are made largely of iron, silicon, magnesium, and oxygen, the kinds of worlds that could support liquid water and stable surfaces become much rarer. At the same time, a stronger electromagnetic force would affect how electrons behave around atoms. Electrons would be pulled in closer to the nucleus. Atomic sizes would shrink. The distances between atoms in a molecule would change. Chemical bonds depend on the overlap of electron clouds, the regions of space where electrons are likely to be found. Shrink those clouds, and the geometry of molecules shifts. Some bonds that are stable in our universe would weaken or break. Proteins, DNA, the complex folded structures that biology depends on, all of them are held together by precise arrangements of chemical bonds. Change the bond lengths and bond angles even slightly, and those structures do not fold correctly. Enzymes stop working. Genetic information cannot be stored reliably. The molecular machinery of life stops functioning. Weaken the electromagnetic force, and the opposite happens. Protons repel each other less. Nuclei become more stable, but atoms become larger. Electrons orbit farther from the nucleus. Chemical bonds lengthen. Molecules become more loosely bound, which sounds harmless until you realize that loose bonds mean less stable compounds. Water might not stay liquid over a useful temperature range. Organic molecules might fall apart too easily under thermal stress. And stars, which depend on electromagnetic interactions to generate the radiation pressure that supports them against gravitational collapse, would behave differently. Their cores would be less resistant to compression. They would burn hotter and faster, shortening their lifespans. Again, the window for stable, long-lived stars narrows. The relationship between the strong force and the electromagnetic force is a balancing act. Both are necessary. Both have to be set to values that allow for stable nuclei, stable atoms, and stable chemistry. And the acceptable range for each one is constrained not just by its own effects, but by how it interacts with the others. It is not enough for the strong force to be strong enough to hold nuclei together. It also has to be strong enough relative to the electromagnetic force, which is trying to push nuclei apart. The ratio matters. Change that ratio and something breaks. Then there are the masses of the particles themselves. The proton has a mass of about 938 million electron volts divided by the speed of light squared. The neutron has a mass of about 939 million electron volts divided by the speed of light squared. The difference between them is only about 1.3 million electron volts, roughly 0.14%. That tiny difference is what makes neutrons slightly heavier than protons, and it has profound consequences. Free neutrons are unstable. Leave a neutron alone, not bound inside a nucleus, and it decays in about 10 minutes. It splits into a proton, an electron, and an antineutrino. That decay process is driven by the weak nuclear force, the one responsible for radioactive decay and certain types of particle interactions. The reason neutrons decay and protons do not is that mass difference. The neutron is heavier, so it has extra energy it can shed by transforming into a lighter proton. Protons, being lighter, have nowhere to go. They cannot decay into a neutron without gaining energy from somewhere else. As a result, protons are stable and neutrons are not, unless they are locked inside a nucleus where the strong force changes the energy accounting and makes the neutron stable. This asymmetry is why the universe has hydrogen. In the early universe, when temperatures were still high enough for neutrons and protons to be converting back and forth into each other constantly, the decay of free neutrons shifted the balance. Neutrons kept turning into protons. By the time the universe cooled enough for neutron decay to stop being offset by new neutron production, there were many more protons than neutrons. When nuclear synthesis began, most of the protons stayed as hydrogen. Some of them combined with the remaining neutrons to make helium. But the ratio was lopsided, about 12 protons for every neutron, which is why we ended up with 75% hydrogen and only 25% helium. If the proton-neutron mass difference were smaller, neutrons would decay more slowly. More neutrons would survive into the nucleosynthesis era. The helium fraction would be higher, the hydrogen fraction lower. Shift the mass difference by even a small amount, and you could end up with 50% helium, 30% helium, or more. Less hydrogen means less fuel for stars, shorter stellar lifetimes, and a faster aging universe. Push it far enough, and you run out of hydrogen altogether, leaving a cosmos dominated by helium and heavier elements with no long-lived stars to light it up. If the mass difference were larger, neutrons would decay faster. Fewer of them would survive to participate in nucleosynthesis. The helium fraction would drop. That sounds like it would give you more hydrogen, which it does, but it also removes one of the building blocks for making heavier elements. Helium is the feedstock for the triple alpha process. No helium means no carbon, no oxygen, no elements past lithium. The universe would be hydrogen and not much else. Stars would burn, but they would not produce the elements necessary for planets or chemistry. Again, you lose. The actual mass difference, 1.3 million electron volts, sits right in the range that produces a universe with plenty of hydrogen, enough helium to seed carbon and oxygen production, and a balance that allows for stars to burn for billions of years while building up a periodic table capable of supporting complexity. The margin is tight, measured in fractions of a percent. It is another dial that has to be set correctly for the rest of the structure to work. And then there is gravity. Gravity is the weakest of the four fundamental forces by an almost absurd margin. The gravitational force between two protons is about 10 to the 36 times weaker than the electromagnetic force between them. You can feel this directly. A cheap magnet can lift a paperclip off a table, overcoming the gravitational pull of the entire Earth. But gravity has one advantage the other forces do not. It is always attractive, and it acts over infinite range. Electromagnetic forces can be attractive or repulsive, and often cancel out in bulk matter. The strong and weak forces only act at subatomic scales. Gravity does not cancel. Every piece of mass in the universe pulls on every other piece, no matter how far apart they are. And because it does not shut off, Gravity is what shapes the large-scale structure of the cosmos. It is why gas clouds collapse into stars, why stars cluster into galaxies, why galaxies group into clusters and superclusters. Gravity built the universe we see. The strength of gravity is set by the gravitational constant, usually written as big G, approximately 6.674 times 10 to the minus 11 cubic meters per kilogram per second squared. That number is tiny because gravity is weak, but its weakness is what makes life possible. If gravity were stronger, stars would form more easily from smaller amounts of gas. That sounds good until you think about what happens next. A star's luminosity, the amount of energy it radiates, scales steeply with its mass, roughly as the fourth power of the mass in some cases. A star twice as massive as the Sun is not twice as bright. It is 16 times brighter. And because it is burning through its fuel so much faster, it lives a much shorter time. The Sun will burn for about 10 billion years. A star with 10 times the Sun's mass burns out in only 10 million years, 1,000 times faster. If gravity were stronger, stars would be heavier on average for a given amount of gas. The main sequence, the stable phase of stellar evolution where stars spend most of their lives, would shift toward shorter lifetimes. A star like the Sun, instead of lasting 10 billion years, might last only a few 100 million. That is not enough time for planets to cool, for oceans to form, for chemistry to organize itself into anything resembling biology. Life on Earth took about 4 billion years to go from single-celled organisms to complex multicellular creatures capable of building tools and writing things down. Cut the stellar lifetime to a few 100 million years, and that runway vanishes. Evolution does not have time to get anywhere interesting. Stronger gravity also means that planets orbiting those stars would be subjected to stronger tidal forces. The habitable zone, the range of distances where liquid water can exist on a planet's surface, would shrink. Get too close, and the star's radiation cooks the surface. Drift too far, and the planet freezes. With stronger gravity pulling everything together more tightly, the orbits would be more compact, and the habitable zones would be narrower bands. Fewer planets would sit in that sweet spot. And even if they did, their stars would burn out before life had time to develop. Weaken gravity, and a different set of problems emerges. Stars would form more slowly and less efficiently. Gas clouds would need to be much larger and denser before they could collapse under their own weight. In a universe with weaker gravity, the threshold mass for star formation increases. Below that threshold, gas clouds just drift. They never ignite. The number of stars that form in a given volume of space drops. Galaxies become sparser, dimmer, less active. Fewer stars means fewer sites for planet formation, fewer opportunities for chemistry to develop in the right conditions. And the stars that do form would burn cooler and slower, which sounds good until you realize that cooler stars are often variable, prone to flares and instabilities that would make nearby planets uninhabitable. Red dwarfs, the smallest and coolest stars, can unleash massive flares that strip away a planet's atmosphere in a geological instant. The habitable zone around a cool star is also much closer in, which means planets in that zone are more likely to be tidally locked, with one face always pointed toward the star and the other facing eternal night. Life under those conditions is not impossible, but it is much harder. The gravitational constant, like the other fundamental constants, sits in a range that allows for stars to form in reasonable numbers, to burn long enough that planets have time to develop interesting chemistry, and to do so without subjecting those planets to extreme tidal forces or runaway instabilities. Make gravity too strong or too weak, and the universe becomes less hospitable, often dramatically so. The range is not infinite. It is bounded on both sides by failures of different kinds, and the observed value sits in the middle of that narrow corridor. Now consider the electron. It has a mass of about 9.109 times 10 to the minus 31 kilograms. That is incredibly small. The ratio of the electron mass to the proton mass is about 1 to 1836. That ratio determines the size of atoms, the strength of chemical bonds, and the structure of molecules. Atoms are mostly empty space. The nucleus sits at the center, containing protons and neutrons. Electrons orbit in clouds around the nucleus, and the size of those clouds is set by the balance between the electromagnetic attraction pulling the electron toward the nucleus and the quantum mechanical properties of the electron itself, including its mass. If the electron were heavier, atoms would be smaller, the electron clouds would contract, the energy levels would shift, chemical bonds would change. Molecules that are stable in our universe might not form or might be less stable. Heavier electrons also mean that the energy required to strip an electron off an atom, the ionization energy, increases. Chemistry depends on atoms sharing or exchanging electrons. Make that process harder, and the diversity of chemical reactions drops. Fewer types of molecules can form. The complexity that allows for biology, for proteins and nucleic acids and all the rest, relies on carbon being able to bond in multiple configurations, on nitrogen and oxygen forming functional groups, on hydrogen bonding holding structures together. Change the electron mass and those arrangements shift. Some might still work, but others would not. The phase space for chemistry shrinks. If the electron were lighter, atoms would be larger. Electron clouds would extend farther from the nucleus. Chemical bonds would be weaker and longer. Molecules would be less tightly bound, more vulnerable to being pulled apart by thermal energy or radiation. Water might not stay liquid over a useful range of temperatures. Organic molecules might fall apart too easily under stress. And lighter electrons mean that the radiation emitted when an electron transitions between energy levels shifts to different wavelengths. The spectrum of light that atoms absorb and emit would change, which affects everything from the colors of stars to the way energy is transported through stellar interiors. Stars depend on photons carrying energy outward from the core. Change the way photons interact with electrons, and the structure of stars changes. Their temperatures, luminosities, and lifetimes all shift. The electron mass, like the other constants, is not something you can tweak in isolation. It is part of a coupled system. The electron mass matters because it affects atoms. Atoms matter because they define chemistry. Chemistry matters because it builds the molecules that make planets, atmospheres, oceans, and eventually life. Every step depends on the one before it, and all of them trace back to the fundamental constants sitting at specific values that allow the whole cascade to work. The constants are interdependent. Change the strong force, and you change the stability of nuclei, which changes the output of stellar nucleosynthesis, which changes the elements available to form planets and chemistry. Change the electromagnetic force, and you change the repulsion between protons in nuclei, the structure of atoms, the strength of chemical bonds, and the behavior of stars. Change the proton or neutron mass, and you change the decay rates of particles, the ratio of hydrogen to helium in the early universe, and the fuel available for stars billions of years later. Change gravity, and you change how stars form, how long they burn, and how planets orbit. Change the electron mass, and you change the size of atoms, the nature of chemical bonds, and the way energy moves through matter. Every constant is a thread in a web. Tug on one thread, and the whole web shifts. The tolerances are not generous. A 2% change in the strong force breaks deuterium. A few percent change in the electromagnetic force destabilizes large nuclei or disrupts chemistry. A small shift in the proton-neutron mass difference changes the hydrogen to helium ratio in ways that starve the universe of fuel or building blocks. A modest increase in gravity shortens stellar lifetimes to the point where life does not have time to evolve. A change in the electron mass alters the architecture of molecules in ways that undermine complexity. These are not hypothetical concerns. They are direct consequences of the physics, mapped out in simulations, calculated from the equations, confirmed by experiment. The universe is not robust, it is fragile. It sits in a narrow region of parameter space, where all the constants happen to line up in such a way that atoms are stable, stars live long enough to forge elements, chemistry has the room to build complex molecules, and time stretches out over billions of years to let all of that lead somewhere interesting. Step outside that region, and the cascade fails. The dominoes stop falling because one of the early ones never stood up in the first place. No stars or stars that burn too fast. No heavy elements or elements that do not bond into molecules. No planets or planets that cannot hold atmospheres. No chemistry or chemistry that cannot build the structures necessary for biology. And all of this traces back to a handful of numbers. The strength of the strong force, the strength of the electromagnetic force, the strength of gravity, the masses of the proton, neutron, and electron, the expansion rate of the universe, the density of matter and dark energy, and the amplitude of primordial fluctuations that seeded the formation of galaxies. Each one has to sit in a specific range, each one depends on the others, and each one is measured to high precision, sitting exactly where it needs to be for the universe to function as a place where observers can exist to ask why the numbers are what they are. That is the fabric of reality. Not some abstract philosophical idea, but the literal mechanical structure of the universe, woven from constants that hold atoms together, forces that shape stars, and particle masses that determine whether chemistry is rich enough to build complexity. Change the fabric and the universe unravels. Stretch it and stars die too young. Compress it and atoms collapse or nuclei blow apart. The fact that the fabric holds, that it supports the weight of galaxies and stars and planets and life, is what physicists mean when they talk about fine-tuning. It is not that the universe is beautiful, though it is. It is that the universe works, and the conditions required for it to work are so narrowly defined that calling it coincidence starts to feel less like an explanation and more like an excuse. So now the question shifts. We have established that the constants sit in narrow ranges. We have shown that those ranges are necessary for structure, chemistry, and complexity. The next question is whether that tells us anything deeper. Is it evidence of something beyond random chance? Is it a clue pointing toward a principle we have not discovered yet? Or is it simply the way things are, observed by creatures who could only exist in a universe where things are this way? That is where the anthropic principle enters the conversation, not as a solution, but as a framework for asking whether the question itself even makes sense. The constants sit where they need to be. The strong force holds nuclei together without burning all the hydrogen in the Big Bang. The electromagnetic force keeps atoms stable without making them collapse or fly apart. Gravity pulls gas clouds into stars without crushing them so hard they burn out in a geological eye blink. The electron has a mass that allows chemistry to be complex and stable. The proton and neutron have masses that differ by just enough to leave the universe with plenty of hydrogen fuel. The cosmological constant is almost exactly zero, off by a factor of 10 to the 120 from what theory predicts, sitting in the one narrow sliver of parameter space where galaxies can form and stars can live long enough to build the elements life requires. Every dial is turned to the right setting. Every constant falls in the narrow range that permits structure, complexity, and observers. And once you notice that pattern, once you see how many things had to go right for any of this to exist, a question forces itself to the surface. Why? Why these values and not others? Why a universe where carbon gets made efficiently, where water stays liquid over a useful temperature range, where stars burn for billions of years instead of millions? Why a cosmos fine-tuned for life? The anthropic principle is one answer to that question. It is not a theory in the usual sense. It does not predict new particles or explain the origin of the constants. It is more like a lens, a way of reframing the question so that the apparent coincidence stops looking quite so mysterious. The core idea is simple. The universe has to be compatible with the existence of observers because we are here observing it. If the constants were different, if the strong force, or gravity, or the electron mass sat outside the narrow ranges that permit complexity, there would be no stars forging heavy elements, no planets with stable surfaces, no chemistry capable of building molecules complex enough to think. There would be no one around to notice that the universe was sterile. We observe the constants we do not because they are special in some absolute sense, but because only universes with these constants can produce creatures capable of measuring them. That is the weak anthropic principle, the WAP, and on its face it sounds almost trivial. Of course we observe a universe compatible with our existence. How could it be otherwise? If the constants were lethal, we would not be here to complain about it. The principle does not explain why the constants have the values they do. It just points out that the set of possible universes we could ever observe is restricted to the subset that allows observers to exist in the first place. It is a selection effect, not a mechanism. The term anthropic principle was coined, or at least standardized, by the physicist Brandon Carter in 1974 during a conference in Poland commemorating the 500th anniversary of the birth of Copernicus. The setting was deliberate. Copernicus had taught the world that Earth is not the center of the universe. Over the centuries, that lesson was extended. The Sun is not the center of the galaxy. The Milky Way is not the center of the cosmos. Our position in space is utterly unremarkable. Cosmology spent the better part of 4 centuries driving home the point that humanity occupies no privileged location. Carter's contribution was to push back gently against the overcorrection. Yes, our location in space is unremarkable, but our location in time and in the space of possible physical laws is not arbitrary. We can only exist in an epoch where stars have had time to forge heavy elements and where those elements have had time to assemble into planets and chemistry and life. We can only exist in a universe where the constants permit that process to unfold. Observing that we are here places constraints on what we can observe about the universe. That is the anthropic principle in its weakest, most defensible form. Carter distinguished between 2 versions: the weak anthropic principle, the one most scientists are comfortable with, and the strong anthropic principle, which makes a much bolder and more controversial claim. The weak version says that the universe we observe must be compatible with the existence of observers at this time and place. The strong version says that the universe must have properties that allow intelligent life to develop at some point in its history. The difference is subtle but important. The weak principle is a statement about observation and selection effects. The strong principle sounds like a statement about necessity, as if the universe is somehow required to produce life, as if that is part of its purpose or design. The weak anthropic principle is mostly uncontroversial. It is a methodological reminder, a way of avoiding mistakes when interpreting data. If you are trying to figure out why Earth sits in the habitable zone of a stable star, why it has liquid water and a protective magnetic field and an atmosphere that does not cook or freeze the surface, the WAP offers a clean explanation. We are here because this planet happens to have the right conditions for life. Billions of other planets do not. We do not observe the universe from one of those planets because nothing on those planets is capable of observing anything. Our presence on Earth is not evidence that Earth is special in some cosmic sense. It is evidence that observers can only arise in places where conditions permit observers to arise. The fact that we find ourselves in such a place is not surprising. It is guaranteed. This kind of reasoning shows up in everyday contexts. If you walk into a room and notice that the temperature is exactly comfortable, you do not immediately conclude that the room was designed for your comfort. You conclude that you chose to stay in the room because it was comfortable. If it had been freezing or boiling, you would have left. The rooms you spend time in are not a random sample of all possible rooms. They are selected by the fact that you can tolerate being in them. The weak anthropic principle applies the same logic to cosmology. The universe we observe is not a random sample of all possible universes. It is selected by the fact that we exist to observe it. That selection effect can explain apparent coincidences that might otherwise seem spooky. Take the age of the universe. We live roughly 13.8 billion years after the Big Bang. That is a long time, but it is not arbitrary. Stars like the Sun take about 10 billion years to evolve from the main sequence into red giants. Rocky planets take time to cool and form stable crusts. Chemistry takes time to organize into self-replicating molecules. Evolution takes time to build complexity. If we had appeared much earlier, say a billion years after the Big Bang, the universe would not have had time to produce the conditions necessary for life. If we appeared much later, say 100 billion years from now, most stars would have burned out and the universe would be a colder, darker place. The epoch we observe is not random. It is selected by the requirement that we exist to observe it. We live in the era when stars are still shining, when heavy elements are abundant, when planets are stable and chemistry is rich. That is not because the universe cares about us. It is because those are the only conditions under which creatures like us can exist to ask why the universe looks the way it does. The weak anthropic principle does not explain why the universe has the constants it does. It does not tell you why gravity is weak, or why the cosmological constant is small, or why the Hoyle state sits at 7.653 mega-electron volts. It just tells you that whatever the explanation is, it has to be consistent with the fact that observers exist. If the constants were lethal, you would not be here to puzzle over them. The fact that you are here means the constants, at minimum, are not lethal. That is all the WAP says. It is a constraint on possible explanations, not an explanation itself. Some critics argue that this makes the WAP tautological. Saying the universe must be compatible with life because we are alive to observe it is just restating the problem in different words. It does not tell you why the constants have the values they do. It does not predict anything you did not already know. It just frames the observation in a way that makes it sound less surprising. You started with the question, why is the universe fine-tuned? The WAP answers, because if it were not, you would not be here to ask. That is true, but it does not feel like progress. It feels like you have replaced one mystery with a truism. The defense of the WAP is that it is not trying to explain everything. It is trying to prevent you from making a specific kind of error. The error is assuming that because the constants appear fine-tuned from our perspective, they must have been fine-tuned by something or someone with intent. The WAP points out that our perspective is biased. We are not random observers. We are observers who can only exist in universes where the constants permit our existence. The fact that we find ourselves in such a universe is not evidence of design. It is evidence of selection. If there are many universes or many regions of space-time with different constants, we obviously live in one of the regions that permits life. We could not live anywhere else. The apparent fine-tuning is an artifact of where we are standing, not a feature of the universe as a whole. That argument only works if there are many universes or many regions with different constants. If there is only one universe, if the constants are what they are everywhere and always, then the WAP does not explain anything. It just describes the situation. The universe has one set of constants. Those constants happen to permit life. We exist. Why did the universe get those constants instead of others? The WAP has no answer. It was not designed to have one. The strong anthropic principle tries to go further. It says that the universe must have properties that allow observers to develop at some stage. Must. Not merely happens to, but must. The phrasing makes it sound like the emergence of life is written into the structure of reality, as if the universe is aimed at producing observers. That is a much stronger claim, and it ventures into territory that makes physicists uncomfortable. Science works by finding mechanisms, causes, explanations rooted in physical processes. The strong anthropic principle sounds teleological, like it is importing purpose into the laws of nature. And once you start talking about purpose, you are no longer doing physics. You are doing philosophy or theology. Brandon Carter did not intend the strong anthropic principle to be metaphysical. His formulation was more cautious. He suggested that the universe might have properties that make the emergence of life inevitable, not because of some cosmic designer, but because of the structure of physical law itself. Maybe there is a deeper principle we have not discovered yet that constrains the constants to life-permitting values. Maybe the laws of physics as we know them are not fundamental, but are emergent properties of some underlying framework that requires them to take the values they do. If that framework exists, then the constants are not fine-tuned in the sense of being randomly selected from a vast range of possibilities. They are determined by the deeper structure, and that structure might have features that make life not just possible, but likely or even necessary. That is speculative. Nobody has found such a framework. Nobody has shown that the constants are mathematically required to take the values they do. The standard model of particle physics contains about 25 free parameters, numbers that have to be measured experimentally because the theory does not predict them. The masses of the quarks, the strengths of the forces, the mixing angles that govern how particles interact. All of them are inputs. You plug them into the equations and the theory tells you what happens. Change the inputs and the theory still works. It just describes a different universe. There is no known principle that forces the inputs to be what they are. The strong anthropic principle is a bet that such a principle exists, and that when we find it, it will turn out to have properties that favor the emergence of observers. But it is only a bet. And until someone discovers that principle, the strong anthropic principle remains a hope, not an explanation. The philosopher and writer Martin Gardner summarized the strong anthropic principle as the claim that life is impossible unless the basic laws are exactly as they are. That phrasing highlights the problem. It makes it sound like the universe is fragile by design, built in such a way that life is a necessary outcome. But necessary according to what? If the constants are fixed by some deeper law, then fine-tuning is not tuning at all. It is just the way things have to be. If the constants are not fixed, if they could have been different, then calling life necessary is just wishful thinking. The strong anthropic principle walks a tightrope between those two positions, trying to say that life is somehow privileged without committing to either a designer or a multiverse. Most physicists find the position uncomfortable because it does not generate testable predictions. It is a statement about the structure of reality that cannot be confirmed or refuted by experiment. There is a version of the strong anthropic principle that goes even further, sometimes called the final anthropic principle. It suggests that intelligent life, once it emerges, will continue to exist and evolve indefinitely, eventually gaining enough power to influence the structure of the universe itself. This version is mostly ignored by working scientists because it is untestable and speculative to the point of being science fiction. It is mentioned here only because it shows how far anthropic reasoning can be stretched once you let go of the weak version's discipline. The weak anthropic principle is best thought of as a selection effect. It does not explain why the constants are what they are. It explains why the constants we observe are compatible with our existence. That is a useful distinction in certain contexts. If you are trying to figure out why we live on a planet with liquid water, the WAP tells you that planets without liquid water do not produce observers to ask the question. If you are trying to figure out why the universe is billions of years old, the WAP tells you that observers can only emerge in universes old enough for stars to forge heavy elements and planets to form. If you are trying to figure out why the cosmological constant is small, the WAP tells you that universes with large cosmological constants do not form galaxies and therefore do not produce life. Those are not full explanations, they are constraints. They narrow the range of possible answers. The WAP says that whatever the ultimate explanation is, it has to account for the fact that we are here. That is not trivial. It rules out certain kinds of answers. It tells you that you cannot explain the constants by appealing to randomness alone unless you also explain why randomness happened to land on life-permitting values. And that is where the multiverse enters the conversation, because the multiverse is one way to reconcile randomness with fine-tuning. If there are countless universes with different constants, most of them sterile, then the fact that we live in one of the rare life-permitting ones is not surprising. It is exactly what the weak anthropic principle predicts. We are not in a typical universe. We are in a universe that can support observers. The multiverse provides the ensemble. The WAP provides the selection mechanism. But without the multiverse, the weak anthropic principle starts to feel circular. You ask why the constants are fine-tuned. The WAP answers that they have to be compatible with observers. You ask why they are compatible with observers. The WAP says, because otherwise you would not be here to ask. The loop closes without giving you new information. You are left staring at the same mystery, just phrased in a way that makes it sound less urgent. The constants are what they are. Life exists. Those two facts are connected, but the connection is descriptive, not explanatory. The tautology objection is the most common critique. The weak anthropic principle is true by definition. It cannot be wrong. But something that cannot be wrong often cannot be right either in any useful sense. It is like saying, I am alive because I have not died yet. True, but not enlightening. The way AP becomes useful only when paired with an independent model that explains why the constants vary, why different regions or different universes might have different values, and why we should expect to find ourselves in one of the rare regions where the values permit life. Without that model, the way AP is just an observation dressed up as a principle. The strong anthropic principle has a different problem. It sounds like it is making a claim about the universe having a purpose or being structured in such a way that life is inevitable. That claim is either trivial or profound, depending on what you mean by it. If you mean that the laws of physics happen to permit life, then the claim is trivial and reduces to the weak anthropic principle. If you mean that the laws of physics are required by some deeper principle to permit life, then the claim is profound but completely unsupported. There is no evidence that such a requirement exists. There is no theory that predicts it. The strong anthropic principle, in its boldest form, is a metaphysical stance. It crosses the line from science into philosophy. Some people find that line interesting. Most physicists prefer to stay on the side where experiments can settle arguments. What the anthropic principle does, in both its weak and strong forms, is shift the focus from the constants themselves to the observer. It reminds us that the data we collect, the universe we see, is filtered through the fact that we exist. That filter is not neutral. It biases what we can observe. And recognizing that bias is important, it keeps you from jumping to conclusions. If you notice that Earth is in the habitable zone of a stable star, the anthropic principle warns you not to conclude that Earth is the center of the universe or that the universe was built for humans. It tells you that your presence on Earth is a selection effect. Billions of planets exist. Most of them are uninhabitable. You live on one of the habitable ones, not because habitable planets are common, though they might be, but because uninhabitable planets do not produce observers. That reasoning is sound as far as it goes. The problem is that it does not go very far. It works well for questions like, why do we live on a planet with water and oxygen? It works less well for questions like, why does the cosmological constant take the value it does? In the first case, there are many planets and we are clearly on one of the rare good ones. In the second case, there is, as far as we know, only one universe. If the cosmological constant is the same everywhere, if there are no other universes with different values, then saying we observe a small constant because large constants do not produce observers does not explain why the constant is small. It just restates the fact that it is. The anthropic principle is best understood as a framework for thinking about fine-tuning, not as a solution. It tells you how to avoid certain mistakes. It tells you what kinds of explanations are consistent with the fact that observers exist. But it does not, on its own, explain why the constants are what they are. For that, you need something more. You need either a physical mechanism that sets the constants to life-permitting values, a multiverse that produces a vast range of values so that some of them are bound to be life-permitting, or a deeper theory that shows the constants are not free parameters at all, but are fixed by some underlying principle. The anthropic principle works in tandem with those ideas. It does not replace them. Some physicists have tried to use anthropic reasoning to make predictions. Steven Weinberg, in a paper published in 1987, used the anthropic principle to estimate the maximum value the cosmological constant could have and still allow galaxies to form. His reasoning was straightforward. If the constant is too large, the universe expands so fast that density fluctuations do not have time to collapse into galaxies. No galaxies means no stars, no heavy elements, no planets, no life. Weinberg calculated the threshold and found that the cosmological constant had to be smaller than about 10 times the value we now measure. At the time, the constant had not been measured directly. The prediction was that if it existed at all, it would be small but not exactly zero. In 1998, observations of distant supernovae confirmed that the constant is indeed positive and small, within the range Weinberg predicted. That is one of the few cases where anthropic reasoning led to a testable, falsifiable prediction that turned out to be correct. But even that success is controversial. Some argue that Weinberg got lucky. The anthropic bound he calculated was loose enough that it would have been consistent with a fairly wide range of values. Others argue that the success validates the anthropic approach and shows that it can be scientifically productive when used carefully. The debate continues. What is clear is that anthropic reasoning, at its best, is a tool. Used well, it can guide thinking and make predictions. Used poorly, it becomes a way of avoiding the hard questions by reframing them as selection effects. The deeper issue is whether the anthropic principle is addressing the right question. When physicists talk about fine-tuning, they are often asking two different things. One is a question about probability. Given all the possible values the constants could have, why did they land on life-permitting values? The anthropic principle answers that by saying we can only observe life-permitting values, so the apparent improbability is an illusion created by observation bias. The other is a question about mechanism. What physical process or principle determined the values of the constants? The anthropic principle does not answer that. It sidesteps it. And for many physicists, the mechanism question is the one that matters. The anthropic principle works if you accept that the constants could have been different. If you believe there is a landscape of possible universes, a multiverse, or a set of different regions with different physical laws, then the anthropic principle provides a way to explain why we live in one of the rare life-permitting regions. We live here because we can only live here. Everywhere else is sterile. The principle becomes a statistical argument. Given a large enough ensemble, some regions will be habitable by chance, and observers will only ever find themselves in those regions. The fact that we are here is not evidence that the constants were chosen or designed. It is evidence that the ensemble exists and that we are not in a typical member of it. But if there is no ensemble, if the universe is unique and the constants are what they are everywhere and for all time, then the anthropic principle does not explain anything. It describes the situation. It says the constants are compatible with life because otherwise we would not be here. True. But why did the universe have these constants instead of others? The anthropic principle has no answer. It was not built to answer that question. It was built to explain why our observations are biased. Without a multiverse or some mechanism that varies the constants, the anthropic principle is just a restatement of the problem. And that is where things stand. The weak anthropic principle is a useful reminder about selection effects. It keeps you from over-interpreting the fact that the universe appears fine-tuned. It works well when there is a large ensemble of possibilities and you are trying to explain why you observe what you observe. The strong anthropic principle is more ambitious, suggesting that the universe must allow for life, but it ventures into metaphysics and has not generated much in the way of testable science. Both versions are tools for thinking about fine-tuning. Neither is a complete explanation, and that is fine. The anthropic principle does not have to solve the problem. It just has to clarify what the problem is and what kinds of answers might make sense. The question of whether the anthropic principle is observer bias or deeper truth depends on what lies beneath it. If the constants are set by a multiverse, if there are countless regions with different values and we simply live in one of the habitable ones, then the anthropic principle is observer bias, pure and simple. We are here because the dice rolled in our favor somewhere, and we happen to land in a universe that works. If the constants are set by a deeper principle, some undiscovered law that constrains them to life-permitting values, then the anthropic principle might be pointing toward that deeper truth. It might be a clue that the universe is structured in a way that makes life not accidental but natural, even inevitable, given the right conditions. And if neither of those is true, if the universe is unique and the constants just happen to be what they are for no reason at all, then the anthropic principle is a description of our ignorance. We do not know why the constants are fine-tuned. All we know is that they are, and we are here because of it. That uncertainty is where the anthropic principle leaves us. It frames the question, it clarifies the constraints, it warns against certain mistakes, but it does not close the loop. The constants sit where they sit. Life exists. The two are connected. The anthropic principle tells you not to be surprised by that connection, but it does not tell you why the connection exists in the first place. And for that, you need to look beyond the principle itself. You need to ask whether the universe is one of many, whether the constants are outputs of a deeper framework, or whether the whole question is misframed. The next step in that journey leads to the multiverse, an idea so vast and strange that it makes fine-tuning look tame by comparison. The anthropic principle works in a multiverse. It gives you a mechanism for selection. Without the multiverse, the principle floats, untethered, a statement about bias with no ensemble to bias against. So if you want to know whether the anthropic principle is just a tautology or something more, the answer depends on what you think exists beyond the one universe we can see. The anthropic principle tells you that the constants have to be compatible with your existence, because otherwise you would not be here to notice them. That is true, undeniably true, but it does not feel like an explanation. It feels like a description. You ask why the universe is fine-tuned, and the anthropic principle answers, because if it were not, you would not be asking. The loop closes. The question gets reframed but not resolved, and for decades, physicists have wrestled with the unsatisfying aftertaste of that answer. It works as a constraint. It tells you what kinds of universes can produce observers, but it does not tell you why this universe, with these constants, exists in the first place. Unless, of course, this is not the only universe. The multiverse hypothesis is the idea that there is not one cosmos but many, an enormous ensemble of separate universes, each with its own set of physical laws, its own values for the fundamental constants, its own history. Most of them are sterile, lifeless. Structures that flash into existence and collapse, or expand into cold, empty voids, or burn out before anything interesting can happen. A tiny fraction, purely by chance, land on constants that permit stars, galaxies, chemistry, and eventually observers. We live in one of those rare pockets, not because the universe was designed for us, but because we can only live in a universe that permits life. The multiverse provides the ensemble. The anthropic principle provides the selection mechanism. Together, they turn fine-tuning from a mystery into a statistical inevitability. This is not a fringe idea. It is not relegated to late-night speculation or science fiction conventions. The multiverse has become one of the leading frameworks for addressing fine-tuning in modern theoretical physics. It emerges naturally from inflation, one of the most successful theories in cosmology. It is baked into string theory, the most ambitious attempt to unify quantum mechanics and general relativity. And it is taken seriously, debated fiercely, and defended by some of the most respected names in the field. It is also, and this is important, almost completely untestable. That tension between theoretical elegance and empirical inaccessibility is what makes the multiverse hypothesis both compelling and deeply controversial. The story begins with inflation. In the early 1980s, Alan Guth, Andre Linde, and others proposed that the universe underwent a brief period of exponential expansion in the first fraction of a second after the Big Bang. Driven by a hypothetical field called the inflaton, space itself doubled in size over and over again in a time span so short that light could not cross a single atom. That burst of expansion solved several long-standing problems in cosmology. It explained why the universe looks so uniform on large scales, why space is flat, and why we do not see certain exotic relics like magnetic monopoles that earlier theories predicted should be common. Inflation was a success. It made predictions that were later confirmed by observations of the cosmic microwave background. The tiny fluctuations in temperature across the sky, the seeds that grew into galaxies, match the pattern inflation predicts. By the late 1990s and early 2000s, inflation had become the standard framework for understanding the early universe. But inflation has a strange feature. Once it starts, it is hard to stop everywhere at once. The idea is called eternal inflation. The inflaton field driving the expansion does not shut off uniformly. In some regions, the field decays and inflation ends. Those regions stop expanding exponentially and settle into the kind of slower expansion we observe in our universe today. But in other regions, the field keeps going. Those regions continue to inflate, doubling and redoubling, spawning new pockets where inflation eventually ends and new universes, or at least new regions with different properties, begin. The process never truly stops. Inflation keeps generating new regions forever, each one a separate bubble, causally disconnected from the others, expanding away so fast that light from one bubble can never reach another. Each bubble is effectively its own universe. And here is where things get interesting. The properties of space inside each bubble, the values of the constants, the types of particles that exist, depend on how the inflaton field decays. In some models, the field can settle into different vacuum states, each one corresponding to a different low-energy physics. Think of it like a ball rolling down a hill. The hill has many valleys, and depending on which valley the ball lands in, the landscape looks different. Each valley is a possible universe. Each one has different constants. And if eternal inflation is correct, all of those valleys get explored somewhere, sometime, across the endless inflating multiverse. This is not a wild extrapolation. It is a prediction that follows from taking inflation seriously and running the equations forward. Andre Linde, one of the architects of inflationary cosmology, has described the eternal multiverse as a natural consequence of the theory. If inflation can start, and if the conditions that allow it to start exist in more than one place or can be recreated by quantum fluctuations, then inflation never fully stops. It just keeps spawning new regions. Alexander Vilenkin, another pioneer in the field, has written extensively on the idea, arguing that eternal inflation is not just possible but likely given what we know about quantum field theory and the behavior of scalar fields like the inflaton. String theory adds another layer. String theory is an attempt to describe all particles and forces as vibrations of tiny one-dimensional strings. The mathematics is elegant but comes with a cost. The equations only work in more than 4 dimensions, 10 dimensions in some versions, 11 in others. The extra dimensions have to be compactified, curled up into shapes so small we cannot detect them directly. The geometry of those extra dimensions determines the physics we observe in the familiar 4-dimensional universe. Different shapes, different physics, and there are a lot of shapes. The number of possible ways to compactify the extra dimensions is enormous. Early estimates suggested something like 10 to the 100th distinct configurations. Later work Combining string theory with other ideas like flux compactification pushed the number much higher. 10 to the 500 is a commonly cited figure, though some researchers argue it could be even larger, possibly 10 to the 1000 or more. This vast collection of possible configurations is called the string landscape. Each point in the landscape corresponds to a different vacuum state, a different universe with different constants, different particles, different forces. Most of those universes are nothing like ours. The constants are too extreme. Stars do not form. Chemistry does not work. Observers cannot exist. But some fraction, however tiny, will land on life-permitting values purely by chance. Combine eternal inflation with the string landscape, and you get a picture of a multiverse almost incomprehensibly large. Inflation generates an endless number of bubble universes. String theory provides a menu of 10 to the 500 or more possible sets of physical laws. Every possible configuration gets realized somewhere in the inflating multiverse. Most of them are sterile. A small number are habitable. We live in one of the habitable ones. The fine-tuning problem dissolves. The constants are not special, they are random. We just happen to live in a universe where the random draw came up compatible with life. That is the multiverse hypothesis in its strongest, most optimistic form. It explains fine-tuning without invoking design or purpose. It turns the cosmological constant problem, the worst prediction in physics, into a non-issue. Yes, quantum field theory predicts a vacuum energy 10 to the 120 times larger than what we observe. But in a multiverse with 10 to the 500 possible vacuum states, some of them will have small cosmological constants. We live in one of those because large cosmological constants do not allow galaxies to form. The anthropic principle does the rest. Selection effect. Done. The framework is seductive. It takes two of the most successful ideas in modern physics, inflation and string theory, and shows that together they predict a multiverse. You do not have to add new assumptions, you just follow the math. And the result is a picture that explains fine-tuning, solves the cosmological constant problem, and ties into broader efforts to unify physics under a single framework. For many researchers, the multiverse is not just an answer to fine-tuning, it is the answer. The only one that does not require you to believe in coincidences so extreme they border on the absurd. But there are problems, deep problems. The first is testability. Science works by making predictions that can be checked with experiments or observations. A hypothesis that cannot be tested is not part of science. It might be true, but if there is no way to confirm or refute it, it sits in the realm of speculation. The multiverse, in most of its forms, is untestable. Other universes, if they exist, are causally disconnected from ours. Light from another bubble universe cannot reach us because the space between the bubbles is expanding faster than light can cross it. There is no telescope you can build, no particle you can detect, no signal you can measure that would tell you whether other universes exist. Some researchers argue that there might be indirect evidence. If two bubble universes collided early in their history, the collision might leave a signature in the cosmic microwave background, a bruise or pattern that we could detect. Searches have been done. No such signatures have been found. That does not rule out the multiverse. It just means that if bubble collisions happened, they either happened in a way that did not leave detectable traces, or they did not happen near us. The absence of evidence is not evidence of absence, but it is also not evidence of presence. The multiverse remains speculative. Sean Carroll, a cosmologist and vocal defender of the multiverse idea, has argued that untestability does not automatically disqualify a hypothesis. Many things in physics are accepted even though they cannot be directly observed. Quarks cannot be isolated. The interiors of black holes are inaccessible. The multiverse, Carroll suggests, should be judged not on whether we can see other universes, but on whether the theories that predict it, inflation and string theory, have independent empirical support. If those theories are tested and confirmed, and if they predict a multiverse, then the multiverse gains credibility even if it cannot be tested directly. That argument has its critics. The physicist George Ellis has pointed out that a theory that explains everything explains nothing. If the multiverse can accommodate any possible set of constants, it loses predictive power. You observe a fine-tuned universe, and the multiverse says, of course, that is what you would observe in a habitable universe. You observe a universe with a small cosmological constant, and the multiverse says, of course, that is what you would observe, because large constants do not produce observers. The framework fits all possible observations after the fact. It is not falsifiable. It does not stick its neck out and risk being wrong. And that makes it feel less like science and more like philosophy dressed in equations. The second problem is the measure problem. In an eternally inflating multiverse, there are infinitely many regions, infinitely many bubble universes. Some of them have constants like ours, most do not. If you want to calculate the probability of observing a particular set of constants, you need to define a measure, a way of counting universes or weighting outcomes. But in an infinite ensemble, the counting gets ambiguous. How do you compare the size of one infinity to another? Which regions do you include? How do you avoid double counting or missing parts of the multiverse that have not inflated yet but will in the future? Different choices of measure give different answers. Some measures predict that we should observe a cosmological constant much smaller than what we actually see. Others predict values closer to observations. Still others lead to paradoxes or divergences where the probabilities do not make sense. The measure problem has been debated for decades, and there is no consensus on the right way to solve it. Without a well-defined measure, the multiverse cannot make precise quantitative predictions. It becomes a qualitative framework, useful for framing ideas, but not for calculating likelihoods. A third problem is the landscape itself. The estimate of 10 to the 500 possible vacuum states comes from string theory, but string theory is not a finished theory. It is a framework, a set of mathematical tools and insights that have not yet been fully developed into a complete, testable model of particle physics. The landscape is derived from assumptions about how the extra dimensions compactify, how fluxes wrap around those dimensions, and how various fields stabilize in different configurations. Those assumptions might be wrong, or incomplete, or too simplified. There is also the swampland conjecture, an idea that emerged in the last decade, suggesting that many apparent solutions in the string landscape are not actually consistent. They look like valid vacuum states on paper, but when you check more carefully, they violate subtle consistency conditions required by quantum gravity. If the swampland conjecture is correct, and that is still an open question, then the landscape might be much smaller than 10 to the 500. Maybe it is only 10 to the 10, or 10 to the 50. Or maybe there are no stable vacuum states at all that look like our universe, and the whole framework collapses. The landscape is not settled science. It is work in progress, built on a foundation that is itself speculative. A fourth issue is that the multiverse does not actually explain why the constants have the values they do. It explains why we observe life-permitting constants by saying that we live in one of the rare universes where those constants happen to permit life. But it does not tell you why the ensemble exists. Why is there eternal inflation? Why does string theory predict a landscape? Why are there 10 to the 500 vacuum states instead of 0 or 1 or infinity? You have replaced one mystery with another. Instead of asking why the cosmological constant is small, you are now asking why the multiverse is structured in such a way that small cosmological constants are possible. The explanatory burden shifts but does not disappear. Some multiverse proponents accept this. They argue that the existence of the multiverse might be a brute fact, something that does not have a deeper explanation. Just as asking why the universe exists at all eventually hits a wall, asking why the multiverse exists might hit the same wall one level up. The hope is that the multiverse framework at least shifts the question to a place where the answer feels more natural. Eternal inflation follows from generic assumptions about scalar fields and quantum mechanics. The string landscape follows from the mathematical structure of string theory. You are not adding ad hoc fine-tuning, you are following where the theories lead. But whether that counts as an explanation or just a repackaging of the mystery is still being argued. The controversy reached a peak in the early 2000s when critics began publishing papers arguing that the multiverse was not science at all, that it was untestable metaphysics masquerading as physics. Defenders pushed back, pointing out that the multiverse was not invented to solve fine-tuning. It emerged from inflation and string theory, both of which have independent motivations and some degree of empirical support. The fine-tuning problem is one application of the multiverse idea, not its raison d'etre. If inflation is correct, and if string theory is correct, then the multiverse follows whether you like it or not. Ignoring it because it is hard to test would be ignoring the implications of your best theories. In 2024, a detailed critique of the fine-tuning argument itself appeared in the literature, arguing that fine-tuning does not clearly favor a multiverse over a single universe. The reasoning goes like this. Suppose the constants are drawn randomly from some distribution. If there is only one universe, the probability that the constants land on life-permitting values is very small. If there are many universes, the probability that at least one of them lands on life-permitting values is much higher. So far, so good. But the question is not, what is the probability that a life-permitting universe exists? The question is, what is the probability that I, as an observer, find myself in a life-permitting universe? In both the single universe and multiverse scenarios, the answer is 100%. Observers can only observe life-permitting universes. The multiverse increases the number of observers, but it does not change the probability that any given observer sees life-permitting constants. The anthropic conditioning works the same way in both cases. The fine-tuning, from the observer's perspective, does not favor the multiverse over a single finely tuned universe. That argument is subtle, and not everyone agrees with it. Some researchers think it misses the point. The multiverse makes fine-tuning less surprising, not because it changes conditional probabilities, but because it removes the need to explain why the one and only universe happened to be life-permitting. If there is only one universe, the fact that it has life-permitting constants demands an explanation. If there are countless universes, the fact that one of them has life-permitting constants is expected. The shift is conceptual, not probabilistic. Whether that counts as real explanatory progress or just a reframing of the question depends on your philosophical commitments. The multiverse also has defenders who argue that it is scientifically legitimate even if it cannot be tested in the traditional sense. Max Tegmark, a cosmologist at MIT, has proposed a hierarchy of multiverse types. Level 1 is the simplest, just the idea that space is infinite and every possible arrangement of matter occurs somewhere eventually. Level 2 is the eternal inflation multiverse, where different regions have different physical laws. Level 3 is the many worlds interpretation of quantum mechanics, where every quantum measurement spawns a branching tree of outcomes. Level 4 is the ultimate ensemble, the idea that every mathematically consistent universe exists. Tegmark argues that multiverse thinking is unavoidable once you take modern physics seriously. You do not choose to believe in the multiverse chooses you. Not everyone is convinced. Paul Steinhardt, one of the early architects of inflation, has become one of the multiverse's harshest critics. He argues that eternal inflation and the string landscape have turned cosmology into a field where anything goes, where every observation can be explained by appealing to some corner of the multiverse. That kind of framework, he says, is not predictive, it is not falsifiable, it is not science. The multiverse has become a crutch, an excuse for not finding a real theory that explains why the constants have the values they do. The debate is fierce, ongoing, and unlikely to be settled anytime soon. Both sides are arguing from defensible positions. The multiverse framework emerges from taking inflation and string theory seriously. It provides a potential solution to fine-tuning that does not require invoking design or accepting an implausible coincidence, but it is also speculative, untestable in most formulations, and vulnerable to the charge that it explains everything and therefore predicts nothing. Whether you find it compelling depends largely on what you think science should be allowed to do. Should it only address questions that can be answered with experiments? Or can it follow theoretical reasoning into domains that are, at least for now, beyond the reach of observation? One thing is certain: the multiverse is not going away. It is too deeply embedded in modern theoretical physics to be dismissed. Inflation predicts it, or at least versions of inflation predict it. String theory requires it, or at least seems to, if you want to explain the diversity of possible vacuum states. And as long as fine-tuning remains an open question, the multiverse will be one of the leading candidates for an answer. It might not be the right answer. It might turn out that inflation does not work the way we think, or that string theory is wrong, or that there is a deeper principle we have not discovered yet that sets the constants without needing a multiverse. But for now, the multiverse stands as the most well-developed framework for turning fine-tuning from a mystery into a statistical expectation. The key insight is simple. If the constants are random, and if there are enough universes, then some of them will land on life-permitting values by chance. We live in one of those because we could not live anywhere else. The multiverse does not explain why the constants are what they are. It explains why we observe the constants we do. That distinction matters. It shifts the focus from the constants themselves to the observers. It turns fine-tuning into a selection effect rather than a design feature. And for many physicists, that shift is enough. It takes a problem that looked like evidence of purpose or intention and makes it look like the natural outcome of a large enough sample size. Of course, large enough is doing a lot of work in that sentence. 10 to the 500 is unimaginably large. The number of atoms in the observable universe is only about 10 to the 80. The number of possible chess games is around 10 to the 120. 10 to the 500 is so large that there is no physical analogy that captures it. You cannot count that high. You cannot visualize it. You cannot even meaningfully compare it to other large numbers. It exists only as an abstraction, a consequence of the mathematics of string compactifications. Whether such a number corresponds to anything real, whether there are actually 10 to the 500 distinct universes out there somewhere, is completely unknown. The multiverse hypothesis asks you to accept the existence of an almost infinite ensemble of universes, most of which are unobservable in principle, in order to explain why the one universe you can see has constants that permit your existence. For some people, that trade-off is worth it. It removes the need for fine-tuning, which feels like a goal worth pursuing. For others, the trade-off is too steep. You are explaining one mystery by invoking a much larger and more speculative structure. You are solving the problem of why this universe exists by saying it does not need an explanation because countless other universes exist too. That might be true, but it is not satisfying in the way that a clean, testable, predictive theory is satisfying. And yet, the multiverse persists. It persists because it fits naturally into the frameworks physicists are already working with. It persists because it provides a response, even if not a fully satisfying one, to the fine-tuning problem. It persists because alternatives are scarce. If you reject the multiverse, you are left with fewer options. You can accept fine-tuning as a brute fact, which feels unsatisfying. You can argue for a deeper principle that constrains the constants, which no one has found. Or you can invoke design, which takes you outside the boundaries of science. The multiverse avoids all three. It is naturalistic, it follows from existing theories, and it does not require you to give up on finding a physical explanation. It just asks you to accept that the physical explanation involves an ensemble too large to ever fully explore. The connection between the multiverse and fine-tuning is often framed as a prediction. If the multiverse exists, fine-tuning is expected. We should see constants that look fine-tuned because we can only observe life-permitting universes. But the inverse is trickier. Does fine-tuning predict a multiverse? Not necessarily. Fine-tuning is consistent with a multiverse, but it is also consistent with a single finely tuned universe. The data alone does not tell you which framework is correct. You need additional evidence, either from inflation or string theory or some other source, to tip the scales. And that evidence, for now, is indirect at best. The multiverse hypothesis is a bold idea. It expands the scope of reality beyond anything humans have ever conceived. It suggests that the universe we see, the one containing hundreds of billions of galaxies and trillions of stars, is just one bubble in an incomprehensibly vast froth of bubbles, most of them empty or hostile, a few of them like ours. It turns cosmology into a kind of cosmic anthropology, the study of which types of universes can produce observers and why we happen to live in one of them. It is ambitious, speculative, and deeply strange. It is also one of the most serious attempts modern physics has made to explain why the constants are what they are. But it is not the only attempt, and it is not, for many, the most compelling. Because the multiverse does not explain where the constants come from. It does not tell you why inflation happens, or why string theory is true, or why there is something rather than nothing. It just shifts the question up one level. And for those who find that shift unsatisfying, there are other answers on the table, some of them even stranger than the multiverse. Some of them stepping outside the boundaries of science entirely, into domains where experiments cannot go and telescopes cannot see. Domains where the question of why the universe is fine-tuned leads not to an ensemble of universes, but to questions about consciousness, computation, and whether reality itself might be something other than what it appears to be. The multiverse hypothesis does not close the door. It opens a larger one. Instead of asking why this universe has constants that permit life, you are now asking why there is a multiverse at all, why eternal inflation happens, why string theory predicts a landscape of 10 to the 500 possible vacuum states. You have replaced one mystery with a bigger mystery, dressed in mathematics but still fundamentally speculative. And for some people, that trade is worth it because the multiverse at least offers a naturalistic framework, something built on physics rather than metaphysics. But for others, the trade feels hollow. You are explaining fine-tuning by invoking an ensemble of universes so vast that it can never be observed, tested, or confirmed. And once you step into that territory, once you accept that the explanation for why things are the way they are might lie forever beyond the reach of experiment, other possibilities start to look less absurd, possibilities that do not involve physics at all. Possibilities that ask whether the universe might be something other than what it appears to be, a simulation, a creation, or a structure governed by laws we have not discovered yet, laws that make the constants not accidental but necessary. These are the other answers, the ones that make physicists uncomfortable because they sit at or beyond the boundary of what science can address. But the discomfort does not make them irrelevant. The fine-tuning problem has pushed cosmology into philosophical territory, whether anyone wanted it there or not. And once you are in that territory, you have to deal with the full range of possible explanations, even the ones that sound strange, even the ones that cannot be tested in a laboratory, even the ones that challenge the assumption that the universe is a purely physical system operating without intention or purpose. Start with the simulation hypothesis. The idea is straightforward. What if the universe is not a naturally occurring physical system, but a computational construct? What if reality, all of it, stars, planets, atoms, the forces that govern them, the constants that define how those forces behave, is software running on hardware we cannot see? A simulation created by some advanced intelligence, something with the computational power to model an entire cosmos down to the quantum level. In that framework, fine-tuning is not a mystery, it is programming. The constants are what they are because someone or something set them to those values. The universe permits life because it was designed to, not by a deity in the traditional sense, but by a programmer, a cosmic engineer. A civilization so far beyond ours that building universes is a routine task, the way we build video games or climate models. This is not ancient mythology repackaged. The simulation hypothesis is a modern philosophical idea launched into public discourse most famously by Nick Bostrom, a philosopher at Oxford, in a paper published in 2003. Bostrom's argument was not that we are definitely living in a simulation, but that at least one of three possibilities must be true. Either civilizations like ours tend to go extinct before reaching the technological capability to run detailed simulations of conscious beings, or advanced civilizations capable of running such simulations choose not to, perhaps for ethical reasons. Or we are almost certainly living in a simulation because if advanced civilizations do run such simulations, they would create so many simulated realities that the ratio of simulated observers to real observers becomes astronomically lopsided. If trillions of simulated universes exist for every base reality, the odds that you are in the base reality are vanishingly small. The logic is airtight if you accept the premises, and the premises are not wild. Computation has been advancing rapidly for decades. The simulations we can run now, weather models, physics engines in video games, neural networks that mimic aspects of human cognition, are crude but improving. Extrapolate that progress forward a few centuries, a few millennia, and it is not hard to imagine a civilization with enough computational power to simulate a universe in fine detail. Not just the visible macroscopic world, but the quantum behavior of every particle, the dynamics of every force, the evolution of every star and galaxy. If such simulations are possible, and if civilizations that reach that level of technology choose to run them, then simulated realities would vastly outnumber base realities. We would, statistically speaking, be more likely to live in one of the simulations than in the original. Fine-tuning fits neatly into that picture. If the universe is a simulation, the constants are inputs, parameters set by the programmer. The question of why they have the values they do is answered the same way you would answer why a video game has the physics it does. Because someone chose those settings. Maybe they wanted to create a universe capable of producing complexity and observers. Maybe they were studying the conditions under which life emerges. Maybe they were just curious. The motivation does not matter. The point is that in a simulation framework, fine-tuning is not accidental, it is intentional. The universe looks designed because it is designed, just not by a god in any traditional sense. By something that exists outside the simulation, operating at a higher level of reality. The hypothesis solves several problems at once. It explains fine-tuning without requiring a multiverse. It explains why the constants are what they are without needing a deeper physical principle, and it does so in a way that is, at least in concept, naturalistic. The simulators are not supernatural beings. They are advanced intelligence, products of their own evolutionary or technological development, running software on hardware. The framework is mechanistic. It just places the mechanism one level up, outside the universe we can observe. But it creates new problems. The first and most obvious is that the simulation hypothesis is untestable in any conventional sense. If you are inside the simulation, you cannot see outside it. The simulators, if they exist, are not part of the physics you are studying. They are not made of atoms. They do not obey the laws of your universe. They exist in a higher reality, the base reality, and by definition, you have no access to it. You cannot run an experiment that would confirm or refute whether you are in a simulation, because the simulation, if it is good enough, would be indistinguishable from a naturally occurring universe. Some researchers have speculated about possible tests. Maybe the simulation has glitches, artifacts of finite computational resources that show up as anomalies in the data. Maybe the resolution of spacetime is quantized in a way that reflects the grid size of the underlying computation. Some physicists have suggested looking for patterns in the cosmic microwave background or in the distribution of high-energy particles that might indicate a computational substrate. So far, nothing has been found. And even if something were found, interpreting it as evidence of a simulation rather than just an unexpected feature of natural physics would be extraordinarily difficult. The second problem is that the simulation hypothesis does not actually answer the question. It just moves it. You ask why the constants are fine-tuned. The simulation hypothesis says because the simulators programmed them that way. Fine. Now ask why the simulators exist. Why does their universe have the properties it does? Why are they capable of running simulations? If their universe also appears fine-tuned, you are back to the same problem one level up. If it does not, if the base reality is fundamentally different in ways that make fine-tuning unnecessary, then you have to explain why that universe is structured so differently from ours. The hypothesis does not close the loop, it shifts the mystery up a layer. The third problem is philosophical. If the universe is a simulation, what does that mean for the nature of reality? Are the stars real? Are the atoms real? Are you real? The objects in a simulation are data structures, patterns of information encoded in the computational substrate of the base reality. They are not physical in the way we usually think of physical. They are abstractions. And if that is true, then the constants are not fundamental properties of nature. They are arbitrary choices made by the programmers. Change the code, and the constants change. The laws of physics are not laws. They are subroutines, and the universe is not a cosmos. It is software. Some philosophers argue that this does not matter. If the simulation is detailed enough, If the experiences it generates are indistinguishable from those of a base reality, then calling it a simulation is a semantic distinction without practical consequence. You still experience pain, joy, thought, consciousness. The stars still shine, chemistry still works. Whether the substrate is atoms or bits makes no difference to the lived experience of being inside the system. Others argue that it matters a great deal. If the universe is software, it can be paused, edited, deleted. The simulators might be running countless versions with slightly different parameters, watching which ones produce interesting outcomes. You might be one iteration in a vast parameter sweep. Your existence might be contingent on whether the simulation is still providing useful data. That is an uncomfortable place to land. The simulation hypothesis has become a popular idea in public discourse, partly because it bridges the gap between science and science fiction in a way that feels modern and tech-forward. It has been discussed by public intellectuals, technologists, and physicists. Elon Musk has said publicly that he thinks the odds we are living in base reality are billions to 1 against. Neil deGrasse Tyson has called the hypothesis plausible. The philosopher David Chalmers has written extensively on how the simulation hypothesis challenges traditional assumptions about the nature of consciousness and reality. It is not fringe speculation. It is a live debate in philosophy of physics and metaphysics. But it is also not science, at least not yet. It cannot be tested with the tools we have. It does not make falsifiable predictions, and it does not integrate cleanly into the frameworks physicists use to understand the universe. The simulation hypothesis is speculative philosophy. It is a possible answer to the fine-tuning problem, and it is worth taking seriously as a logical possibility, but it does not offer the kind of explanatory closure that a physical theory provides. It trades one set of mysteries for another and asks you to accept the existence of a layer of reality that is forever out of reach. Then there is the other answer, the one that predates the multiverse, the anthropic principle, and the simulation hypothesis by thousands of years. The idea that the universe was created, designed, intentionally structured by an intelligence that exists outside of time and space. God, in the traditional theological sense, a being with the power to set the constants, to define the laws, to build a cosmos capable of producing life. The fine-tuning problem in this framework is not a problem at all, it is evidence. The universe looks designed because it is designed. The constants sit in narrow ranges because they were chosen, set deliberately to permit the emergence of stars, planets, chemistry, and eventually creatures capable of recognizing the design and giving thanks for it. This is the teleological argument, one of the oldest arguments for the existence of a creator. It dates back at least to ancient Greece, to thinkers like Plato and Aristotle, and it has been refined and debated for centuries. The modern version of the argument points specifically at fine-tuning as evidence. The constants are not random, they are precise. They sit in narrow ranges that allow for complexity. The probability of landing on those ranges by chance, if the constants were selected randomly from all possible values, is so small that coincidence becomes implausible. The universe appears fine-tuned because it was fine-tuned. And the most straightforward explanation for that fine-tuning is intention. A designer, a creator. The argument has serious defenders within philosophy and theology. The Stanford Encyclopedia of Philosophy notes that many researchers see fine-tuning as support for a cosmic designer, and that this version of the teleological argument is considered by some to be the strongest case for theism available in modern discourse. The constants are measured. The ranges are narrow. The sensitivity is real. Those are empirical facts, not matters of faith. The interpretation of those facts as evidence of design is where the philosophy comes in. and for many, that interpretation is compelling. The universe does not look random, it looks structured, ordered, built with intention. But the design argument has problems too. The first is that it does not specify what kind of designer. If you accept that fine-tuning points to a creator, you still have to explain what that creator is, where it came from, and why it chose to create a universe with these particular constants. Is the creator the god of any specific religious tradition? Is it a deistic god that set the constants and then stepped back, letting the universe run on its own? Is it something else entirely, a cosmic architect with no resemblance to anything described in human theology? Fine-tuning might suggest design, but it does not tell you who or what the designer is, and without that, the argument remains incomplete. The second problem is that the design hypothesis is scientifically untestable. If the designer exists outside of space and time, if it operates beyond the reach of physical law, then there is no experiment you can run to detect it. You cannot measure God. You cannot build a telescope that looks outside the universe. You cannot collect data on the intentions or methods of a being that is not made of matter and does not interact with the physical world in measurable ways. The design hypothesis explains fine-tuning by invoking something that cannot be studied scientifically. And for most scientists, that is where the conversation stops, not because they think the idea is wrong, but because they think it is outside the scope of what science can address. A 2024 paper in Theological and Philosophical Literature argued that fine-tuning can be read within classical metaphysics as contingent evidence pointing toward divinity, but not as proof. The constants are contingent. They could have been different. The fact that they are what they are suggests they were set by something, but it does not demonstrate that something is God in the full theological sense. The argument is probabilistic, not deductive. It raises the likelihood that a designer exists, but it does not close the case, and it does not rule out alternative explanations like the multiverse or the simulation hypothesis. The design argument also has to contend with the problem of unnecessary suffering. If the universe was designed by a benevolent creator, why is it structured in such a way that allows for pain, disease, death, natural disasters, mass extinctions, black holes, supernovae, cosmic rays, and the eventual heat death of everything? Fine-tuning permits life, sure, but it also permits suffering on a cosmic scale. If the designer could set the constants to any values, why not choose values that permit life without permitting suffering? That question is a version of the problem of evil, and it has been debated in theology for millennia. Fine-tuning does not resolve it. If anything, it sharpens it. A universe fine-tuned for life is also a universe fine-tuned for entropy, decay, and eventual oblivion. The theological perspective on fine-tuning is not monolithic. Some traditions see the constants as evidence of divine providence, a sign that the universe was crafted with care. Others see them as consistent with, but not proof of a creator, part of a larger tapestry of evidence that includes revelation, religious experience, and moral intuition. Still others argue that fine-tuning is a distraction, that focusing on physical constants misses the deeper theological point about why anything exists at all rather than nothing. The design argument is not settled even within theology. It is one possible interpretation of the data, and it competes with others. From a scientific standpoint, the design hypothesis is not an explanation, it is a stopping point. It says the constants are what they are, because a designer set them that way, and then it stops. It does not tell you how the designer did it, what mechanisms were used, what principles governed the choices. It does not generate testable predictions. It does not integrate with the rest of physics. It stands outside the framework of natural law. invoking an agent that operates by fiat rather than mechanism. And for most physicists, that is unsatisfying. Science works by finding natural explanations, by tracing effects back to causes that can be studied, measured, and tested. The design hypothesis cuts that chain. It appeals to an uncaused cause, something that sets the constants without being subject to any higher principle. And once you do that, you have left science behind. That does not mean the design hypothesis is wrong. It means it is not scientific. It exists in a different domain, one where questions of purpose, intention, and meaning are primary. Many people find that domain compelling. Many find the fine-tuning evidence persuasive as a pointer towards something beyond the natural world. But within the practice of science, the design hypothesis does not offer the kind of explanatory purchase that theories like the multiverse or deeper physical principles promise. It is an answer, but it is not a scientific answer, and that distinction matters. Which brings us to the third possibility. The idea that the fine-tuning problem is not actually a problem because the constants are not free parameters at all. What if there is a deeper theory, a more fundamental framework that fixes the constants to the values they have? What if the constants are not arbitrary settings, but necessary consequences of some underlying structure that we have not discovered yet? In that picture, asking why the constants are fine-tuned is like asking why the interior angles of a triangle add up to 180 degrees. They do because that is how triangles work in flat space. It is not a coincidence, it is a consequence of geometry. Maybe the constants are consequences of some deeper principle, some symmetry or conservation law or mathematical necessity that forces them to take the values they do. This is the dream of a theory of everything, a unified framework that explains all four fundamental forces, all the particles, all the constants, starting from a single set of principles. String theory is one candidate. Loop quantum gravity is another. There are others, less well known, more speculative. None of them are complete. None of them have been confirmed experimentally. But the hope is that when we finally crack the code, when we find the deeper theory that underlies quantum mechanics and general relativity, the constants will fall out as predictions rather than inputs. They will be fixed by the structure of the theory itself. And once that happens, the fine-tuning problem disappears. The constants are not fine-tuned, they are determined. Albert Einstein envisioned something like this. He is quoted by the Stanford Encyclopedia of Philosophy as saying that a future theory might contain only rationally, completely determined constants, meaning that the constants would be fixed by fundamental principles rather than tuned by chance. Einstein believed that the universe was comprehensible, that its laws were not arbitrary, that there was a reason why things are the way they are. He spent the last decades of his life searching for a unified field theory that would explain electromagnetism and gravity from a single framework. He did not find it, but the hope persists. The hope that the constants are not accidents, not random draws from a vast parameter space, but inevitable outcomes of some beautiful mathematical structure. The problem is that no one has found that structure. String theory, the leading candidate for a unified theory, predicts a landscape of 10 to the 500 possible vacuum states, each with different constants. That is the opposite of what you want if you are trying to fix the constants. Loop quantum gravity is still under construction and has not yet produced a full description of particle physics. Other approaches are even less developed. The theory of everything remains a dream, a goal that has eluded physicists for a century. And without it, the hope that the constants are fixed by deeper principles is just a hope. There is no evidence for it, no mechanism, no framework that does the work. There is also the possibility that the constants are related to each other in ways we do not yet understand. Hidden connections, deeper symmetries, relationships that constrain the values so that once you set one constant, the others follow. Some researchers have looked for such relationships, searching the data for patterns, correlations, mathematical structures that might hint at an underlying constraint. So far, nothing conclusive has been found. The constants appear to be independent. Change one and the others do not adjust. There is no known symmetry that ties them together. But that might just mean we have not looked in the right way. The history of physics is full of examples where relationships that seemed random turned out to be consequences of deeper principles. Electromagnetism and the weak nuclear force were unified in the 1960s. The strong force was brought into the fold with quantum chromodynamics. Maybe the constants are next. The limits of current scientific inquiry are real. Physics has been stuck on certain problems for decades. The cosmological constant problem has been unsolved since the 1980s. The hierarchy problem, why the weak force is so much stronger than gravity, has no answer. The nature of dark matter and dark energy remains mysterious despite decades of searching. The unification of quantum mechanics and general relativity has been a goal for a century and remains out of reach. Science is powerful, but it is not omnipotent. There are questions it cannot answer yet, and there might be questions it cannot answer ever, not because the answers do not exist, but because the tools and frameworks available to us are insufficient to reach them. Fine-tuning might be one of those questions. It sits at the boundary of physics, philosophy, and metaphysics. The data is clear, the constants are what they are, and they sit in narrow ranges that permit complexity and life. The interpretation of that data is where things get murky. Is it evidence of a multiverse, of a simulation, of a designer, of a deeper principle? Or is it just a brute fact, something that requires no explanation because it is simply the way things are? Each of those answers has strengths and weaknesses. None of them are fully satisfying. None of them close the loop cleanly. Philosophy has a role to play here because the question of why the constants are what they are is not purely empirical. It is also conceptual. What kind of explanation would count as satisfying? What kind of answer would make the mystery go away? Those are philosophical questions, and they shape how scientists and thinkers approach the problem. The multiverse appeals to those who want a naturalistic explanation that avoids invoking design. The simulation hypothesis appeals to those who are comfortable with the idea that reality might be layered, with our universe existing inside a larger computational framework. The design hypothesis appeals to those who see the universe as purposeful, structured by intention rather than chance. The deeper theory hypothesis appeals to those who believe the universe is comprehensible, that its laws are not arbitrary but necessary. Each framework reflects different assumptions about what the universe is and what kinds of explanations are legitimate. And until we have more data, better theories, or new ways of testing these ideas, the debate will continue. Fine-tuning is not going away. The constants are not changing. The question of why they have the values they do will keep being asked, and the answers will keep being debated, because the question touches on something fundamental. It asks not just how the universe works, but why it works the way it does. And that is a question that sits at the intersection of science, philosophy, and something deeper. Something that every human culture has grappled with in one form or another since people first looked up at the stars and wondered where it all came from. The simulation hypothesis, the design hypothesis, and the hope for a deeper theory are not alternatives to the multiverse. They are part of the same conversation, different ways of responding to the same mystery. The universe appears fine-tuned. That is the fact. What it means, where it points, and what we should do with that information is where the frameworks diverge. None of them are complete. None of them are proven. And all of them, in their own way, are trying to make sense of a cosmos that seems balanced on a knife's edge, held together by constants so precisely set that shifting any one of them would cause the whole structure to collapse. Whether that precision is accident, design, programming, or necessity is the question. And the answer, if there is one, will reshape not just our understanding of the universe, but our understanding of our place within it. The multiverse says the constants are random, and we live in a lucky pocket. The simulation hypothesis says the constants are programming, and we live in software. The design argument says the constants are intentional, and we live in a creation. The Anthropic principle says the constants have to be compatible with observers, because otherwise there would be no one here to notice them. The hope for a deeper theory says the constants might not be free parameters at all, that they could be fixed by some principle we have not discovered yet. Each of these answers has been defended by serious people. Each of them addresses part of the problem, and none of them closes the case. That is where we are, decades into the fine-tuning debate, with more data than ever before, with telescopes that can see to the edge of the observable universe, and particle accelerators that can probe the structure of matter at scales smaller than a proton, and the central question remains open. Why do the constants have the values they do? Why does the cosmological constant sit at 1 part in 10 to the 120 instead of the value quantum field theory predicts? Why does the Hoyle state sit at exactly the energy level needed for stars to make carbon? Why is the strong force strong enough to hold nuclei together, but weak enough that hydrogen survives the Big Bang? Why is gravity weak enough that stars burn for billions of years instead of millions? Why does the universe permit complexity, chemistry, and life when the vast majority of possible parameter settings would produce sterile voids or brief flashes of energy that collapse before anything interesting can happen? These are not rhetorical questions, they are empirical puzzles. The constants are measured. The ranges are known. The sensitivity is real. Change any one of the constants by a modest amount, and the universe stops working as a place where observers can exist. That is the fact. What it means is where the disagreement begins. And the disagreement is not going to be settled anytime soon, because the problem sits at the boundary of what science can address. It touches on questions about the nature of reality, the existence of other universes, the possibility of design, the limits of physical law, and the role of observers in shaping what we can know about the cosmos. Those are not easy questions. They are not the kind of questions you answer with a single experiment or a clever equation. They are foundational. They go to the heart of what it means to do science and what kinds of explanations we should be willing to accept. The multiverse is the most developed scientific response. It follows from inflation, one of the best tested frameworks in cosmology. It connects to string theory, the leading attempt to unify quantum mechanics and gravity. It turns fine-tuning from a mystery into a statistical expectation by positing that there are countless universes with different constants, and we live in one of the rare ones that permits life. The Anthropic principle handles the selection. We are not in a typical universe. We are in a universe where observers can exist, and that is the only kind of universe we could ever observe. The framework is elegant. It is naturalistic. It does not require design or purpose or anything outside the realm of physics. It just requires that the ensemble exists. But the ensemble is unobservable. Other universes, if they are real, are causally disconnected from ours. They are not just far away. They are unreachable in principle. The space between bubble universes in an eternally inflating multiverse expands faster than light. No signal can cross it. No telescope will ever see another universe. No experiment will ever confirm that they exist. The multiverse is a prediction of certain theories, but it is not a prediction that can be tested directly, and that makes it feel less like science and more like metaphysics. You are explaining one mystery, fine-tuning, by invoking a much larger structure that itself has no explanation. Why is there eternal inflation? Why does string theory predict a landscape? Why are there 10 to the 500 possible vacuum states instead of 1 or 0? The multiverse shifts the question up a level. It does not answer it. The simulation hypothesis does the same thing. It explains fine-tuning by saying the constants are inputs set by a programmer. That works. It accounts for the data. But it leaves you asking who the programmers are, where they came from, why their universe permits them to exist, and whether their reality is also a simulation running on some even higher substrate. The hypothesis is internally consistent. It might even be true, but it is not testable, and it does not give you closure. It just moves the mystery into a domain you cannot reach. The design argument is older and more straightforward. The universe looks designed because it is designed. The constants are set by a creator, an intelligence with the power to build a cosmos capable of producing life. The argument has philosophical weight. It has theological resonance. It has been defended for centuries, but it is not scientific. It appeals to an agent that operates outside of natural law, that cannot be studied or measured, that does not make predictions you can test in a lab. The design hypothesis explains the constants by invoking something that itself requires no explanation, an uncaused cause, a first mover. And once you do that, you have stepped outside the framework of science. That does not make the hypothesis wrong. It makes it non-scientific. It belongs to a different conversation, one where questions of meaning and purpose are central rather than peripheral. The hope for a deeper theory is more modest. It says maybe the constants are not free parameters. Maybe they are fixed by some underlying principle, some symmetry or mathematical structure that forces them to take the values they do. If that principle exists, fine-tuning is not tuning at all. It is just the way things have to be. The constants are determined the same way the interior angles of a triangle are determined in flat geometry, not by chance, by necessity. That would be a beautiful resolution. It would mean the universe is comprehensible in the deepest sense, that its structure is not arbitrary but follows from logic or mathematics or some framework we have not discovered yet. But no one has found that framework. The constants appear independent. There is no known principle that ties them together. The theory of everything remains elusive. And without it, the hope that the constants are necessary rather than contingent is just a hope. Each of these answers has defenders. Each of them addresses part of the problem. The multiverse explains why we observe life-permitting constants without invoking design. The simulation hypothesis offers a mechanistic account of how constants could be set. The design argument points to the apparent intentionality behind the structure of the universe. The deeper theory hypothesis keeps open the possibility that the constants are not random but determined by something more fundamental. And the anthropic principle, in its weak form, reminds you that your observations are biased, that you can only find yourself in a universe compatible with your existence, and that apparent fine-tuning might be a selection effect rather than evidence of anything deeper. But none of them are complete. None of them have been proven. None of them have achieved consensus. The multiverse is speculative. The simulation hypothesis is untestable. The design argument is non-scientific. The deeper theory does not exist yet, and the anthropic principle, on its own, is just a constraint on possible explanations, not an explanation itself. You are left staring at a set of options, each with strengths and weaknesses, none of them fully satisfying, and that is uncomfortable. Science is supposed to provide answers. It is supposed to resolve mysteries, to replace ignorance with understanding. But the fine-tuning problem has resisted that process. It has been studied for decades. The data has gotten better, the theories have gotten more sophisticated, and the mystery remains. That does not mean science has failed. It means science has reached a boundary. The kind of boundary where empirical methods, powerful as they are, cannot go further without new tools, new frameworks, or new ways of thinking about the problem. The constants are what they are. We can measure them to extraordinary precision. We can model what would happen if they were different. We can show that the ranges permitting life are narrow. But we cannot, with current methods, determine why they have the values they do. The answer, if there is one, lies outside the reach of experiment. It might lie in a multiverse we cannot observe. It might lie in a layer of reality we cannot access. It might lie in a principle we have not discovered. Or it might not have an answer at all, in the way we usually think of answers. Maybe the constants are just brute facts. Maybe asking why they are what they are is like asking why the universe exists at all. Eventually, you hit a wall. Eventually, you run out of explanations, and you are left with existence itself, unexplained and perhaps unexplainable. The philosopher Gottfried Leibniz posed the question centuries ago: why is there something rather than nothing? That question has never been answered satisfactorily. Fine-tuning is a variation on the same theme. Not why is there something, but why is the something structured in this particular way, with these particular constants, permitting this particular outcome? And like Leibniz's question, it might not have an answer that fits neatly into the framework of science. It might be a question that forces you to confront the limits of what can be known, to accept that some mysteries do not resolve, that some features of reality are simply given rather than derived. That acceptance is not defeat, it is humility. It is recognizing that the universe is under no obligation to make sense to us, to fit into categories we find comfortable, to provide explanations that satisfy our desire for closure. The cosmos existed for billions of years before humans appeared. It will exist for trillions of years after we are gone. It does not care whether we understand it. It does not care whether the constants feel fine-tuned to us or whether we find that unsettling. It just is. And we, briefly, improbably, against all odds, are here inside it, awake and capable of asking why. The fine-tuning problem is not going to be solved in this video. It is not going to be solved in the next decade. It might not be solved in your lifetime, but that does not make it unimportant. If anything, it makes it more important, because the fact that the problem is hard, that it sits at the intersection of physics, philosophy and metaphysics, that it forces you to think about the nature of reality and your place within it, is exactly why it matters. Easy questions get answered and then you move on. Hard questions linger. They shape how you think about everything else. They define the boundaries of what you know and what you do not know. And they remind you that the universe is far stranger, far larger, and far more mysterious than any story we can tell about it. There is a temptation, when faced with a mystery this deep, to pick a side and defend it, to commit to the multiverse, or the design hypothesis, or the simulation idea, and treat it as settled, to stop wrestling with the uncertainty and plant a flag on one explanation. But that temptation should be resisted. The fine-tuning debate is live precisely because none of the answers are conclusive. The data underdetermines the interpretation. The constants are fine-tuned in the sense that they sit in narrow ranges. What that means, why it is true, and what we should do with that information are still open questions. And staying open to multiple possibilities, uncomfortable as that is the honest position. Science works best when it holds competing ideas in tension, testing them, refining them, looking for ways to distinguish between them. The multiverse might be testable in indirect ways. Maybe future observations of the cosmic microwave background will reveal signatures of bubble collisions. Maybe advances in string theory will narrow the landscape and make specific predictions. Maybe inflation will be confirmed or refuted by new data. The design hypothesis might gain traction if other lines of evidence, theological or philosophical, converge with the scientific observations. The simulation hypothesis might become more plausible if we develop our own capability to run detailed simulations of conscious beings and realize that doing so is not as far-fetched as it sounds. The deeper theory might emerge from work on quantum gravity, loop quantum gravity, or some other framework that has not been fully developed yet. Any of these could shift the conversation. None of them are locked in. What is locked in is the data. The constants are measured. The fine-tuning is real. And that fact alone is worth sitting with, because it tells you something profound about the universe. It tells you that the cosmos is balanced on a knife's edge, that the difference between a universe capable of producing stars, galaxies, planets, and life, and a universe that is sterile and empty comes down to a handful of numbers sitting in very specific ranges. Shift the cosmological constant by a factor of 10 and galaxies do not form. Weaken the strong force by 2% and stars do not make carbon. Strengthen gravity and stellar lifetimes drop to a few 100 million years. The margin is thin, the tolerance is narrow, and yet here we are, existing, observing, asking why. The sense of wonder that comes from confronting that fact is not a side effect of the fine-tuning debate. It is the point. Wonder is what drives science. It is what keeps researchers working on problems that might not be solved for decades or centuries. It is what makes you look at the night sky and feel awe instead of indifference. The fine-tuning problem, whatever its ultimate resolution, gives you a reason to feel that awe. It shows you that the universe is not a random jumble of stuff obeying arbitrary laws. It is a structure, a system, a fabric woven from forces and constants that somehow, improbably, permit the existence of complexity and consciousness and the capacity to ask questions about your own origins. You are made of atoms forged in the cores of dying stars. Those atoms are held together by forces whose strengths were set in the first moments after the Big Bang. Those forces built the periodic table, which built chemistry, which built biology, which built brains capable of wondering why any of this exists. The chain is unbroken. Every step depends on the one before it, and every step depends on the constants sitting exactly where they need to be. You are not an accident in the sense of being random noise. You are a consequence, a result of a universe that, for reasons we do not fully understand, permits the kind of structure necessary for things like you to exist. That does not tell you whether the universe was designed, or whether you live in a multiverse, or whether reality is a simulation. It just tells you that you are here, that your existence is improbable, and that the improbability is rooted in the fundamental constants that define how everything works. Whether that improbability is evidence of something deeper or just a statistical fluke in a vast ensemble is the question. And the question, more than any specific answer, is what makes the fine-tuning problem so compelling. The physicist Richard Feynman once said that he would rather have questions that cannot be answered than answers that cannot be questioned. That sentiment applies here. The fine-tuning debate is full of answers that cannot be fully tested, frameworks that make sense in some ways but fall short in others, ideas that are provocative but incomplete, and that is fine. Better to have a live debate with multiple perspectives than to prematurely close the conversation by declaring one answer correct. The multiverse might be real, design might be real, a deeper theory might emerge, or the constants might just be what they are, brute facts that require no explanation because they are the starting point for everything else. All of those are possibilities, none of them are certainties. And living with that uncertainty, embracing it rather than fleeing from it, is part of what it means to engage seriously with the question. There is also something liberating about not having a final answer. It means the conversation is still open. It means there is room for new ideas, new data, new ways of thinking about the problem. The fine-tuning debate is not stuck, it is active. Researchers are still working on it. Papers are still being published, theories are still being refined, and every once in a while, something new shows up in the data that shifts the landscape. The discovery that the cosmological constant is positive, that the universe is accelerating, was one of those shifts. It turned the cosmological constant from a theoretical curiosity into an empirical fact, and sharpened the fine-tuning problem in a way that could not be ignored. The next shift might come from advances in particle physics, from better measurements of the constants, from progress in string theory or loop quantum gravity, or from some completely unexpected direction. The point is that the story is not over. You are living through a moment in history when the deepest questions about the universe are being asked with unprecedented clarity. The tools are better than they have ever been, the data is richer, the theories are more sophisticated, and the mystery is as deep as ever. That combination, the power of modern science colliding with the limits of what can be known, is rare. It is the kind of moment where real progress happens, where frameworks shift, where new ideas take root. The fine-tuning problem is at the center of that moment. It connects cosmology, particle physics, philosophy, and theology. It forces you to think about the nature of reality, the role of observers, and the question of whether the universe has a purpose. And it does so not through speculation, but through measurement. The constants are data. The ranges are empirical. The sensitivity is quantified. The fine-tuning problem is grounded in the hardest kind of science, even as it pushes into the softest kinds of questions. That duality is what makes it so fascinating. You start with numbers, the strength of the electromagnetic force, the mass of the electron, the value of the cosmological constant, pure physics. And you end with questions about why anything exists, whether the universe was made for us, whether we are alone, whether there is meaning built into the structure of reality. Those are not questions you can answer in a lab. But they are questions the lab forces you to ask. The data leads you there. The fine-tuning is not something you choose to see. It is something you notice because the measurements are precise and the consequences are clear. And once you notice it, you cannot unnotice it. You have to deal with it. You have to figure out what it means. The fact that we do not have a final answer yet is not a failure, it is a feature. Science is not about accumulating a fixed set of truths. It is about asking better questions, refining your understanding, testing your assumptions, and being willing to change your mind when the evidence points elsewhere. The fine-tuning debate is science doing what it does best, taking a mystery seriously, exploring multiple explanations, holding ideas loosely enough that they can be revised or discarded if necessary, and staying curious even when the answers do not come easily. So where does that leave you? You have learned that the universe is fine-tuned in the sense that the constants sit in narrow ranges. You have seen that the cosmological constant is wrong by a factor of 10 to the 120, and yet sits exactly where it needs to be for galaxies to form. You have learned that the Hoyle state is tuned to within a fraction of a percent, allowing stars to make carbon efficiently. You have seen that the strong force, the electromagnetic force, gravity, and the masses of particles all fall into ranges that permit structure, chemistry, and complexity. You have explored the multiverse as a response, the anthropic principle as a framework, the simulation hypothesis as a possibility, and the design argument as a perennial alternative. You have considered the hope that a deeper theory might one day explain why the constants are what they are, without needing a multiverse or a designer. And you have arrived here, at the end of the conversation, with no definitive answer. Just a deeper appreciation for the mystery. The universe permits your existence. That is not guaranteed. It is contingent on a set of numbers that could have been different. And the fact that they are not different, that they are set in such a way that stars shine and planets form and chemistry builds complexity and life asks questions, is either the luckiest accident in the history of existence or evidence of something deeper. Which one it is depends on what you think lies beyond the edge of observation, beyond the reach of experiment, beyond the boundaries of the cosmos we can see. The fine-tuning problem is not going away. It is part of the fabric of modern cosmology. It is baked into the data. It is embedded in the equations. And it is asking you personally to think about what it means that you are here, that the universe is structured in such a way that your existence is possible, and that the margin between existence and non-existence is so breathtakingly thin. You do not have to have an answer. You do not have to pick a side. You just have to sit with the question. Let it shape how you see the universe. Let it remind you that the cosmos is far stranger than common sense suggests, that the constants defining reality are not arbitrary, and that your presence here, reading this, thinking about this, is one of the most improbable outcomes the universe has ever produced. That improbability is not a reason to despair. It is a reason to pay attention, to look harder, to ask better questions, to embrace the uncertainty and see it not as a gap in knowledge, but as an invitation. The fine-tuning problem is not solved, but it is understood, it is measured, it is mapped. And the fact that it exists, that the universe is balanced in this precise and delicate way, is one of the most profound discoveries science has ever made. Not because it gives you an answer, because it gives you a question worth spending a lifetime thinking about. You exist because a handful of numbers fell into place with a precision that defies comfortable explanation. The cosmological constant sits at 1 part in 10 to the 120th of where theory says it should be. The Hoyle state rests at exactly the energy level that allows stars to forge carbon. The strong force holds nuclei together without incinerating all the hydrogen in the Big Bang. Gravity pulls gas clouds into stars without crushing them so hard they burn out before planets have time to form. The electron has a mass that permits chemistry to be complex enough to build molecules capable of asking why any of this is here. Change any one of those settings by a few percent and the cascade stops. No stars, or stars that die too young. No carbon, or carbon that gets burned into oxygen before it can seed the cosmos. No atoms stable enough to bond into the structures that biology requires. The universe does not become slightly less interesting, it becomes sterile, a void. A flash of light that fades before anything can notice it ever happened. We do not know why the constants are what they are. We have frameworks, the multiverse, the anthropic principle, the simulation hypothesis, the possibility of design, the hope for a deeper theory that makes the constants inevitable rather than accidental. Each of those answers solves part of the problem and leaves the rest untouched. None of them close the loop. None of them give you the kind of satisfaction that comes from understanding something completely. And maybe that is the point. Maybe the universe is not required to make sense to you. Maybe the fact that you are here, improbable as it is not evidence of anything except that the dice rolled and you happen to land in a pocket of reality where the constants permit observers. Or maybe it is evidence of something deeper, something we have not found yet, something waiting at the edge of what we can measure and test and know. Either way,